Okay, Bismillah ar-Rahman ar-Rahim. Alhamdulillah Rabbil Alameen. Wassalatu wassalamu ala Rasulillah wa ala alihi wa sahbihi ajma'in. I'd like to welcome the Vice President, Dr. Ali Sheikhi, our respected guests, faculty, and colleagues from the industry, students. You are most welcome to our forum titled Integrated Communication and Sensing. So in the quick introduction, we will just make sure that we take you through a few things. In a few seconds, I'll be leaving the floor to Dr. Ali Sheikhi, our Vice President. I'll just highlight that the introduction will go over the forum structure, the schedule. We'll listen to our Vice President for research and innovation, and then we'll start with our program right away. The program is featured with two main sessions. The focus, the title, of course, is Integrated Communication and Sensing, and the theme is Green Communication and Sensing. The first session has two speakers, Professor Amin Moeness and Professor Henk, and the second session also has two respected speakers. We will conclude with the panel discussion, which takes about 15 minutes just to conclude the main ideas. We are very honored to have very renowned speakers and very well-known speakers, including Professor Amin Moeness from Villanova University, Professor Henk from Chalmers University from Sweden, and then we have also Professor Gregory from Georgia Institute of Technology, and Dr. Ahmed Alkhateeb from Arizona State University. This is a nutshell about the program and how it works. We'll have a chance after listening to Dr. Ali Sheikhi to thank our organizing committee. So Dr. Ali, the floor is all yours.
Thank you very much, Dr. Mugabil, for the introduction. First of all, it really gives me an immense pleasure and honor to welcome you all, the attendees, to this important forum about the integrated communication and sensing. Also, I'd like to welcome our distinguished speaker, and I'd like really to thank, I'll take the opportunity to, before Dr. Ali Mugabil, to thank the committee that arranged for the meeting, to thank them, all the committee members that arranged for and organized this workshop. As you can see them, Dr. Muhammad Zahid, Dr. Wissam Misbah, Muhammad Al-Hassoun, Dr. Azzuddin, Dr. Lawal, Mr. Pervez Khan, and of course, the Director, Dr. Ali Mugabil. So thank you all for this important workshop. Let me just take this opportunity to inform you that KFUPM went through an amazing transformation in the last 2 years. Starting from January 2020, we started with the academic transformation, in which that the university introduced really a number. We updated all our undergraduate program and also introduced new department. We launched a number of programs, specialized program like the CX program, which is the specialty program for the undergraduate, the MX program, which is the professional master degree. A number of them, around 30 each of these programs have been launched, plus so many other programs and activity. And also we started our amazing journey for our research transformation as well. And we are happy that we introduced a number of centers. These centers, we introduced them based on, we did really an excellent job and our homework that we studied everything. We studied the industry outside, the university outside, the vision of KFUPM, the needed, the community around us, also the capability of our university and the faculty member. And based on really an extensive search of all of that, we came up with those centers. So we introduced around over 16 centers, spanning those areas as you can see them: Center for Advanced Material, Membrane and Water Security, Intelligent Manufacturing, as you can see, all of them. The main thing that the objective of this research transformation is really to have an impactful research. We don't want just the research to produce papers. We want a research that is of benefit to the kingdom, to the benefit of our society and the community and to the benefit of the humanity. So we introduced a number also of programs. We enhanced our capacity building in terms of the human resources, the faculty member. We are now attracting top-notch faculty member from around the world. We enhanced also our postdoc, the number of postdoc. We are targeting over 200-300 postdoc. Also our graduate students, we are enhancing the number of graduate students because they are the driving for the research. And also not to forget the innovation part, in which that we introduce a number of services that will help our faculty member to achieve the goals that we set, in which that we need really our research to benefit our society. And these programs include, for example, proof of concept, the Entrepreneurship Institute, the seed fund for venture capital that can help making our prototypes and offer it to the industry for further investment, and so on and so forth. So we are now, I think, in the right directions for achieving our goals. So these centers, one of the centers, of course, here is the Center for Communication System and Sensing. And I'm really happy that this workshop is about combining both the communication system and sensing, and you are in the right direction actually by suggesting this center. And you can see that the mission and the challenges and the themes of the center, ranging from the communication system, the localization, the signal processing, the sensing, and the combination of those together. And this comes also, as I mentioned, the importance of this workshop, which is the integrated sensing and communication, the ASAC. And this is really important to combine sensing and the communication system to utilize the wireless resources efficiently, realize the wide area environment sensing, and even to pursue mutual benefits. And also, it's the co-design of communication system and sensing that will allow for the considerable gains in terms of spectral, energy, hardware, and cost efficiency. And this is very much aligned even with the grand challenges of the centers, ranging, for example, from developing these holistic designs like the drones and the anti-drones, plus also the green communication as well, which is really, I think, the focus of this workshop. This is also in alignment with the vision of the Kingdom of Saudi Arabia, Vision 2030, in the communication sector, with the Saudi Arabia securing its position to be in the top 10 nation with the highest internet speed. And the vision also addresses the reduction of emission and efficiency and green use of the resources as well. And also the university research sector has realized the importance of this topic. And as mentioned, we dedicated this interdisciplinary research center for communication system and sensing. And the center is contributing to the topic through the integrated communication and sensing with a focus on green aspect. Without any further ado, since I have only 10 minutes, I hope that we really have an excellent workshop, forum, and it will be fruitful for everybody. Looking forward really to have more of these, and also thanking everybody for attending and for the arranging for this. And also, I don't want to forget KICS, which is our KFUPM Institute for Knowledge Exchange, that actually disseminate our knowledge to the world. Thank you very much, everybody, and I hope that you'll enjoy this workshop.
Thank you very much, Dr. Ali, our Vice President for Research and Innovation. And I think just not to waste more time, I'd like to encourage everybody to visit us in the Center for Communication and Sensing. Please come, stop by, visit and chat, and hope to find a point for collaboration. I leave now the floor to Dr. Mohamed Zahid, who's our chair for the committee for organizing the forum. So, Dr. Zahid.
Thank you very much, Dr. Ali Muqabil, and good afternoon, everyone. So I will be the moderator for this forum. So now let's kickstart our first session. So the first session, session 1, which is Green Communication and Sensing 1. The chair of the session will be Dr. Azadeen Zarguin, and our first speaker will be Dr. Moeness. Dr. Azadeen, maybe you can take the floor and you can introduce the speakers.
Yeah, thank you, Dr. Zahid, for the presentation. Here we have today Dr. Moeness Amin with us. Professor Moeness Amin received the BS, his bachelor degree from the Faculty of Engineering, Cairo University in 1976, his master's degree from King Fahd University of Petroleum and Minerals in 1980, and his PhD degree from the University of Colorado, Boulder in 1984, all of them electrical engineering. Since 1985, he has been with the faculty of the Department of Electrical and Computer Engineering, Villanova University, Villanova, Pennsylvania, where he became the director of the Center of Advanced Communication, College of Engineering in 2002. He is Professor Moeness Amin is a fellow of many societies, including the IEEE, and Professor Moeness has so many achievements, including the latest one which he has received just 2 days ago, the recipient of the 2022 IEEE Dennis Picard Medal in Radar Technologies and Application. He is the author of more than 850 journal and conference publications, and also he has co-authored 20 books, chapters, and is the editor of 3 books on radar. The floor is to you, Professor Moeness.
Well, I would like to thank Professor Azadeen and Professor Ali for inviting.
Just 1 minute.
Go ahead, take your time.
Well, I would like to thank Professor Azadeen and Professor Ali for inviting me to give this short talk about coexistence between radar and communications, maybe from a different perspective. So the title is Cognitive Radar, the Perception Action Cycle from Radio Frequency Coexistence Perspective. Certainly is a very broad area, but I picked up just a couple of examples, knowing very well that Professor Ali's interest in sparse arrays and Professor Azadeen's interest is in adaptive signal processing. So I try to just bring those 2 areas to bear under the umbrella and the auspices of coexistence. So the outline, we're going to give just a general introduction of RF coexistence, provide a view of radar communication coexistence. So coexistence can cover many RF services. So we're just going to focus on radar and communications. We're going to give you a couple of examples. We're going to look at the perception action cycle, and we'll give you an example, very simple example about the integrated radar and communications, right? It's called directional modulations, and then we're going to conclude. So the motivations of coexistence is certainly, the radar is becoming more and more sophisticated, demanding more bandwidth. At the same time, the civilian communications also are becoming very hungry for more bandwidth. So there is a clash between those 2 areas. And the only solution is to coexist and provide uncontested frequency bandwidth. So in general, really, radar is the one that's losing to the commercial interest behind the communication revolution, right? Because it's profit-driven. So solution of spectral congestion by providing uncontested shared bandwidth between radar and communications, that's certainly the only way out. Needs for bold and new concepts with the potential to precipitate significant improvements in the efficiency of radio spectrum utilization and protection from interfering services. That's the main goal. Simultaneously, operations of radar target illumination and wireless services using the same frequency bandwidth, a drive that is referred to coexistence enabled by cognitive radio. Right? So we're going to give a different perspective, coexistence and different components and different strategies. One of them is certainly integrated communications and sensing. So I want to put this in perspective. So there are three references here. I believe that will give the listener or the people who's watching this presentation a good review. So those three papers provide different perspectives, again, for the same topic, which is coexistence. So again, as I said, coexistence between many RF surfaces, including radar communications, radio telescopes, telemetry, satellite navigations, satellite communications, terrestrial satellite. So these are all RF services, and we're going to focus on those two, which is radar and communication. So the question here, how you share the bandwidth, right? So this is my own take about it. I mean, you can share the bandwidth as if you're sharing an apple, right? This half is mine, this half is yours, and everybody goes his own way. Or you can do what's called spectral dynamic sharing, which is basically as if you are having a house. Everybody's entitled to use the same room. A room here is the bandwidth. But you cannot be in the same room at the same time, right? So that is called dynamic spectral sharing. Here we go. And basically, you can see the blue and the red. So the blue is radar communications are the red. These are bandwidth and certainly time. So time segment and bandwidth, and they don't overlap. So if you take a look at communications signals and radar signals, and systems, you will see commonality, you see differences. And this slide just lists the main principal features, if you will, of each system. So, I mean, the main features are very well known. So here, this is actually extracted from one of the references that I co-authored and appeared in the Digital Signal Processing Journal, I think last year, 2021. So you can see here the radar coexistence, right? You can look at cooperative and non-cooperative. Yeah. The integrated radar communications fall under cooperative. So the cooperative is that understanding between the two services, such as that no one interferes with the other. That is cooperative, right? The non-cooperative is, there is a primary and there is a secondary, right? The primary has the right of way, and the secondary has to yield, right? So the non-cooperative, there are interference suppression techniques that must be provided. So this is actually taken from, again, from the revised standards of definitions of radar. This is IEEE STD 686 in 2017 is being revised. I just draw your attention that the integrated radar communication is part of the cooperative radar coexistence. Right? So I'm giving you the overarching definition of coexistence, under which so many other definitions fall. So if you take a look again under each of cooperative and non-cooperative, you will see there is some other subcategories. For example, under cooperative, there is a co-design and there is a dual function. So the co-design, that could be, again, an integrated radar communications. Basically, from inception, the radar people and communication people get together and say, listen, we'd like to design a waveform that's good for you, good for me, and all the things, right? Power sharing and all the things is the same platform. The dual function is certainly the way we defined it, is that there is a legacy system, right? Let's say the radar is operational, and then the communication come in and say, can I use your system, right? Can I use your signals, right? So in the communication field, they call it radar-centric and communication-centric, but we defined it earlier than them, right? We said dual function radar communication. When you say R before C, you would say that actually the radar is the legacy system, is the host, and the communication is trying to use the resources. If you say dual function communication radar, that means communication is the host and radar trying to take advantage of it, right? And then if you go to the non-cooperative, you will see that there are also several categories that come under it. So as you can see, when if you say, well, I am the radar, I am operating, I'm very happy with what I have, then the communications come in and say, well, can I use your waveforms? Can I use your beam? Can I use your power? Can I use your array, right? That means the communications are trying to use the resources that the radar enjoy. So we know what the radar does: sends a periodic signal, hits the target, comes back, reflections. They have a CPI, the coherent processing interval. They try to do the FFT, try to get higher SNR and get the Doppler, and then they also move the beam right and left in order for tracking. These are the radar resources, and the communications are welcome to use these resources, all of them, or some of them, or subset of them, or one of them, as long as does not cause tremendous alteration to the radar function and performance. So the non-cooperative, you have a primary and you have a secondary. When the radar is a primary, then he's going to go on with its own business, and if there are interferers out there, they're going to take care of it by nulling in the frequency domain, by nulling in the spatial domain. If there is a time domain nulling, that you can have all of them depending on the nature of the interference itself. So here's just a picture showing you that the nulling is done in the frequency domain, and usually communication signals are narrow band relative to the radar signal. So you can see you can notch it in the frequency domain, but also you can do nulling, and Professor Izzeddin certainly in adaptive filtering, you can see that depending on which one is primary, which one's the secondary. So you can see the one on the right, the primary is actually the communications, and trying to, the primary is the radar, which is a plane, putting a beam towards it all the time. And as the communication transmitter moves around, it puts a null in that direction. On the left is the other way around. So you can utilize a spatial domain. Secondary, which is really, so again, if you take a look at the secondary, which is really the cognitive radar, when you talk about cognitive radar from the coexistence point of view, you're talking about the radar as a secondary, not as a primary, right? So the radar has to sense. So recent global regulatory practices have focused on the spectrum auctions to simultaneously earn revenue, of course, it's profit-driven, right, and promote the proliferation of commercial communication systems. And then the C-band, certainly everybody is eyeing it. These regulatory actions have prompted a possible role reversal. So instead of the radar being a primary, because it's a critical technology, now they're telling the radar, listen, you know, communications are primary, and then if, in fact, the bands are vacant, then you are welcome to step in and use them, okay? But this requires the radar to modify both its transmitter and receiver for opportunistic. So the radar becomes an opportunistic RF services, right? It goes after vacant bandwidth, and those bandwidths provide an opportunity for the radar to utilize them. So the cognitive radar, this definition is basically it learns from the environment, and depending on what it learns, it modifies its parameters. And I gave you a slide about the possible parameters: the beam, the signal, the power, you know, all of the things. But in addition to that, it can actually reconfigure itself, and that comes to the sparse arrays, right? Professor Ali recently is looking into it, right? So you can modify the array structure depending on the environment. I'll give you an example for that in a few minutes. So, so if you look at the diagram, so the perception action cycle for a cognitive radar as a secondary from the coexistence perspective. It learns the environment, learns which bands are vacant, which bands are busy, occupied, and then it tries to modify its parameters. So it learns, then it senses, it learns, it acts. Action can be action on the transmitter, or action on the receiver, or action on both. So here, I'll give you an example of action on the receiver. So the perception action cycle underpins and underlies the cognitive radar. So you can say here, sense number one, learn and decide, and then adapt. In what fashion you're going to adapt? You change the radar parameters in order to live with the communications, which now is the primary. So in order to sense, you need spectral sensing, right? So the radar spectral sensing is a paradigm shift for effective non-cooperative spectral sharing. I give you an example for cooperative. So I give you two examples. So those are the two examples. One, we're going to give you a co-design example, which falls under integrated communications radar, and give you another example for the non-cooperative, where the radar acts as a secondary. So that's basically what I said. So if you take a look at that, and this is really a real problem, and I picked that example because, again, the recent interest in KFUPM on sparse arrays, right? So that's actually very fascinating, which basically you start with a sparse array because you want to sense the environment, you want to find out where the sources are. That's angle of arrival estimation, right? Or direction of arrival estimation, right? So in order to do so, we all know that sparse arrays, if properly designed, can give you an opportunity to sense more sources than sensors, right? And Professor Ali is an expert on that. So we're going to start with the configuration that will allow us to give the maximum, the longest co-array sense. I'm going to talk about it in a second, right? So after you sense the environment, right, you do direction finding, and then you know where are the sources. Now you would like to learn about those sources. You will have to find out, is this LTE, is this Wi-Fi, is this, is this that, right? Because if you know the signal ID, you know the bandwidth that they're occupying. And if you know the bandwidth, you can step in as a radar, and if they are vacant, you can occupy them. By the way, this is on the down link and uplink at the same time. So after you learn about where are the sources, now you would like to isolate that. And that's what Professor Azzedine now comes in, is adaptive beamforming. So you would like to put a beamformer towards source A, get the signal. From the signal, you're going to put the signal into a classifier, a DNN, deep neural net classifier. Then now you got the source, you know where it is, and you got its signal. That is really the loop. But the sparse array that is optimal for direction finding, which basically Professor Ali is doing, is not the same sparse array that's optimal to isolate source A. Is not the same sparse array to isolate source B. The configuration is different because the second one, you like to isolate, you would like to maximize signal to interference and noise ratio. This is not the same criterion that when you design a sparse array for direction finding, that's not the same criterion for that. So a good sparse array for direction finding may not be as good in isolating the different sources, as you will see. So you go back and reconfigure the array. So the perception action cycle and array configuration perspective. From a sparse array perspective, Professor Ali, right? So you sense the environment with the best array configuration, say co-prime, nested array, this 1 dimension, 2 dimension, whatever you want to do, right? Learn the direction information, apply the music, apply the sparse construction, apply the spree, apply the beamforming, apply anything you like, right? After you apply, now you know where the sources are. Now it's time to isolate them. Put a beam towards source number 1. Get the maximum SINR. Right? So to get the maximum SINR, you need to configure the array and make it environment dependent. Because now I have a covariance matrix, I have this, I have the power, I have all of the things I need now to maximize SINR for each source separately. So there is an optimum sparse array configuration for each source separately. Right? Sometimes you say I want to design a sparse array, one common sparse array that on average maximizes the SINR. Again, that array is not a co-prime array, is not a nested array, right? It's not any of the famous arrays that people use when they design a sparse array that's not environment dependent. So the sparse array is basically you place your antennas not necessarily in a uniform way, but you put them as such that it maximizes the length of the virtual array. So in general, the sparse array can be divided into structure arrays, and that's, I guess, Professor Ali is focusing on it, right? That's co-prime and nested and all the things, right? This is environmental independent, has nothing to do where the sources are, where the jammers are. It has something to do with give me the maximum length co-array. And then that's what you use for direction finding. Then you move to the second category of sparse array, which is basically the non-structure array. That's environment dependent. That will depend on which source is your interest, which source is your interference, and so forth, so on. So the structure arrays, the co-prime and nested and minimum redundancy array and so forth, so on, we're going to use those for direction finding. Now, once we know the directions, we're going to reconfigure the array, and we're going to use a non-structure array. We're going to design new arrays to maximize the SINR for the source of interest. So again, when you have a physical array, we all know the relationship between the spatial covariance matrix and the temporal covariance matrix. So Rx is related to RSS, and the A matrix is the steering matrix, the columns of which are the steering vectors, and the steering vectors are a function of where the antennas are. If I vectorize, so if you want to do direction finding on the physical array, be my guest. That is your equation here. Okay. Now, what we do is that we say, well, wait a minute, if you vectorize that matrix, you come up with an expression that's really very close to the original expression on the top, but now with certain differences. So instead of snapshots, you have the power, right? And instead of A matrix, which is a steering matrix, you have what's called the co-array matrix, right? And the co-array matrix is much longer than the steering matrix. So for example, A is the steering matrix where each column is the steering vector, and the exponent in each steering vector is the location of the sensor. Once you vectorize that, you create a new matrix, a virtual matrix. Now, the exponent does not have the location. It has the difference of the location. That's why they call it difference co-array. Right? And you want to maximize the length of that vector, right? That's the length of the virtual array, right? So what you like is, as much as possible, include all possible differences. So you want to place your sensors such that you cover all possible differences of the sensor locations, right? If you cover all possible sensors, that means called, a fully augmented array. That means, you didn't leave anything. But if a difference is missing, then you call it a whole, right? So that means it's not fully augmented. So if you take a look at the minimum redundancy array, you have 4 sensors. You place them as sensor 1, 3, 5, and 6. 1, 3, 6, and 7. 1, 3, 6, and 7. If you place this 1, 3, 6, and 7, let's now find out what are differences you can get. Of course, the sensor by itself, that's difference 0, right? Then you get, here is difference 1, difference 2, difference 3, difference 4, difference 5, and difference 6. That means you got all the differences. That is the minimum redundancy array. It's called the redundancy because each difference appears only once, and each difference corresponds to the autocorrelation function. So that is a very powerful, very simple sparse array design. I mean, you have the choice. You wanna apply music to the physical array, or you wanna apply music to the co-array. That is, of course, we're gonna apply music to the co-array because it's a longer aperture, right? So that means allows you to deal with more sources than sensors. Again, you can use any direction finding you like in this specific case, because the perception action cycle, you need to learn and act so quickly before the environment changes. So, having a matrix and doing eigenstructure or inverting a matrix, I mean, there's no time for that. So the interest is, can you do it so fast, right? Because beamforming is the only one that is very well known to be fast. One of the non-beamforming techniques is iterative techniques that reduce the bias and things because of the window. That's called fast iterative interpolated beamforming. I'll give you the references here. But you can use anything you like. So back to this example. So you have 4 sensors, and you have 6 sources. So a physical array cannot help you. You have to go to the co-array, right? Learn about the 6 sensors. I mean, each sensor here, these are communication emitters, right? So you have the QAM, you have the PSK, you have the binary phase shift keying, right, at different angles. So you can see here the powerful, right? So the continuous curve is that if I do FFT to the co-array, right, so it doesn't resolve the 6 sources. But if I do this fast iterative interpolated beamformer, it reduces the bias. So you can see now the vertical lines, it got you 6 sources using 4 sensors. Okay, just imagine that. Now, after you learn about the 6 sources, now you want to isolate them, right, through an optimum beamformer, maximizing the SINR. That's actually Capone beamformer. Right? So that's exactly what we're going to do, right? So we're going to go and we will design a sparse array. That means the configuration and the weights, such as that I maximize SINR for source 1, for example. Right? So this is actually optimization problem that iteratively solved, and there are many techniques well known to do so. But there's no time in perception action cycle. There's no time for iterative techniques, right? So that is why we try to resort to neural net, right? Because in neural net, you shift the complexity to the training data, right? So once you have the neural net, then into testing, it's a straightforward multiplication and sum and all the things. So we apply this neural net now to design the sparse array. So the output of the neural net, if it is 1, that means that sensor that I like. If it is 0, that sensor that I don't like. Right? Of course, I mean, it's not 1 and 0, but it's going to be between 0 and 1. You pick up the highest, the highest numbers. So you can see here we design now a sparse array to maximize SINR for the first source, right, which has this modulation here. So we compared the minimum redundancy array that was very good for direction finding, but no longer good for SINR. Right? And then with the optimum SINR, and then we compare that uniform linear array. Right? If you look carefully, you will see that in the constellation, the optimum SINR configuration actually works the best. And the same thing for the other source. You can see the constellation. The uniform linear array, of course, is the worst. And even for the phase shift keying, you know, you will see that the more the concentrated cluster belongs to the optimum SINR. So this is one example that combines the sparse array design for direction finding and the sparse array design for signal isolation and identification. Right? So that's a perception action cycle. The action here is to reconfigure the array to isolate the sources. The second one, which is very straightforward, which I call it actually under the integrated design of communication and radar, and that's actually very straightforward, very simple. There was a paper in the radar conference just a month ago in 2022, but I'm working with the group in Baylor. So basically, what it is it's actually very simple and kind of fascinating, right? So you have weights, right, in transmit beamforming, right? So what they're going to do is saying that I'm going to choose those weights such that I have n users that I want to communicate n symbols to them, n messages. So what is the best way to do that? Well, you know, if you know where the users are, because these are your friends, right? You know their directions for finding a lot of things, right? If you don't know, if the user doesn't have a bearing, it has a channel, right? So user 1, H1, you estimate the channel, right? So you can replace the columns of this matrix by the corresponding channels, right? H1, H2, H3, right? But R, the one to the right here, these are the messages you want to send to those users. W is the beamforming weights on the transmit. H is the channel matrix. Of course, I mean, if you have a direct line of sight, then you have the steering vectors. Then you can solve it. You can solve for the weights. This is only a set of weights, only one set of weights, right? Such that it will send the messages to the corresponding users, right? That has the steering vector. So if you have R equal HW, you can, you know, depending on the dimension, either it's a simple inversion or pseudo inverse, right? So you can see here on the figure on the bottom to the left that successfully R, by the way, can be any constellation. I mean, user 1 can have one constellation, user 2 can have, right? But at a certain time, you want to send this message to user 1, send message. These messages are in vector R, right? Whether it is body efficient keying or QAM or anything you like. Right? So this is called directional modulation, and it's very simple. Again, people like the fast computation, so that could be very simple. And by the way, it has a property of if you're sending message to your friend 1, your friend 2 as an eavesdropper will not really get that message. So you will see the BER, that the BER is the lowest for the intended user. For other eavesdroppers, it's very high. So in conclusion, I was told that to half an hour. I tried to present to you a coexistence strategy, bringing in current interest in KFUPM, which is sparse array design and adaptive beamforming. And both of them are very vital to the coexistence of radio frequency communication between radar and communication. So I will be very happy to answer questions later on when the things is displayed. Well, I thank you very much.
Thank you, Professor Moeness, for this presentation concerning a timely subject. I don't know if Professor Moeness is with us or not. If he is not, then I can forward you his email address, and then you can ask him about this topic and also other, related things. I don't know, Dr. Zahid, is Dr. Moeness with us or not?
Dr. Azzuddin, I don't see Dr. Moeness,
Yeah.
the attendees as well.
Yeah.
Moeness, if you are in the attendees, can you raise your hand?
No, Professor Moeness is not here.
He is not here.
Yeah. So what we can do, we will forward his email address to the attendees, and if they have any query, and any other related, questions, please forward them to him. He was supposed to be with us because he was just arriving from San Diego to his place in Pennsylvania. He was attending because he got the medal from the IEEE Dennis Picard Medal in radar technologies. So it's I don't know if he informed me that he will be attending with us, but since he's not now, then we can just move to the next lecture.
Dr. Azzuddin, if I may add, maybe the attendees can also write down their questions in the Q&A box.
Yeah.
This can also be a possibility, and later if Dr. Moeness is around, then he would be able to answer it. Besides, sharing the email address to the attendees. Thank you.
Okay. Okay, good. Good suggestion. Should we go for the second lecture?
Yes, Dr. Azzuddin, I think we are.
Yes,
Okay.
please.
All right. Can you just take this one? Yes. I guess Professor Henk is with us, isn't he?
Good afternoon. Yes, I'm here. Hi, Professor Azzuddin.
Very good. Okay. So it is our. Can I start, Dr. Zahid?
Yes, Dr. Azzuddin, you can start.
Yeah, I will just introduce Professor Henk. Professor Henk Wymeersch obtained his PhD degree in electrical engineering, engineering and applied sciences in 2005 from Ghent University, Belgium. He is currently a professor of communication systems with the Department of Electrical Engineering at Chalmers University of Technology, Sweden. He is also a distinguished research associate with Eindhoven University of Technology in the Netherlands. Prior to joining Chalmers, he was a postdoctoral researcher from 2005 until 2009 with the Laboratory of Information Detection Systems at the Massachusetts Institute of Technology. Professor Wymeersch served as an associate editor for IEEE Communication Letters, IEEE Transaction of Wireless Communication, and IEEE Transaction on Communications. And he's currently a senior member of the IEEE Signal Processing Magazine editorial board. Since during 2019-21, he was an IEEE distinguished lecturer with the Vehicular Technology Society. His current research interests include the convergence of communication and sensing in a 5G and beyond 5G context. I'll give the floor to Professor Henk for his lecture entitled Leveraging RIS-Enabled Smart Signal Propagation for Solving Infeasible Location Problems. You have the floor, Professor Henk.
Thank you. And first of all, thank you, Professor Azzuddin, Professor Ali, for the invitation to present this work here. So this talk is related to positioning and the use of intelligent services for so-called green localization, so localization with minimal infrastructure. And the work here is based on a paper where I linked the archive link here, which was led by Dr. Kamran Kehosravi, who's now at Ericsson Research. By the way, can you confirm that you can see the slides and you can hear me properly?
Yes, yes.
Okay,
yes,
very good. Thank you. All right, so there's now a big push, both in research but also in standardization, towards 6G positioning. And a reasonable question to ask is, what do we envision that 6G will bring? And in this picture, which I took from one of my colleagues from the University of Barcelona, Gonzalo Seco, he draws basically the different deployment regimes on the y-axis and different positioning uncertainties on the x-axis. And you see that there's different radio technologies here, 2G, 3G, 4G, 5G, and also GNSS, wireless LAN, Bluetooth, and so forth. And you can see that 6G is this green blob here, which is envisioned to provide centimeter level accuracy for positioning in kind of indoor environments and also to some extent dense outdoor urban environments where GPS typically fails. So we will see today in this lecture why this is possible and also how intelligent services can help to realize this vision. So this is the outline of the talk. I will spend very briefly a few slides on the foundations of radio localization sensing, how it works currently in 5G systems, and then the bulk of the talk is related to the use of reconfigurable intelligence services for localization, in particular for unlocking problems that could not be solved without this technology. And then I'll end with some research questions and challenges. So first of all, in terms of the foundations, so this picture shows a kind of functional decomposition of what's happening in positioning and to some extent also in sensing. So we've just seen this talk on cognitive radar. In positioning, you have this also similar kind of acting and sensing cycle. So we start basically first from a signal shaping part where we design a transmit waveform in time, frequency, and space. And this is true for both positioning and sensing. This is typically a pilot signal, so it doesn't convey any data directly. Then we transmit the signal over the air. It is received by either a remote source or a co-located source if it's from a monostatic radar. Then there's a channel parameter detection and estimation solution. So you detect the number of targets, the number of propagation paths, and then estimate the geometric parameters of each of the paths, angles and delays, for instance. Then depending on the type of application, there's a data association problem because you have a number of angles and delays. You need to relate them to things that you've previously seen, previously detected targets, for instance. After that, you will do an update on the target locations as well as an update on the sensor location. And for instance, in positioning, the sensor location would be the UE device. So the pictures on the bottom show two examples of this. So on the bottom left is a typical monostatic radar, which transmits here an FMCW waveform, hits another car, and then bounces back to the transmitting radar where it's then received and down converted. And then from this received waveform, you can estimate first angles and delay. So that's this channel parameter detection and estimation problem. And then convert this to tracks, where you track an object over time. The figure on the right shows how localization is done using several base stations with different kind of measurements. For instance, here, RTT, these are time-based measurements, as well as angle-based measurements where a base station illuminates different areas of the environment with directional beams. And then this fusion of angle and delay provides positioning estimates. And then, of course, yeah, these are different functions and you can do research in each of these areas. So in our group, we work on all of these aspects in some detail. In terms of the specific measurements that you can take, the most typical form of measurements are time-based measurements. So the figure on the right tries to show that there's a source, in this case a base station, sending a signal to a receiver, in this case a user device, and then the receiver estimates the arrival time of that signal, and this arrival time, which we denote by tau, is proportional to the distance over the speed of light, plus a clock bias. And this is because the user is typically not synchronized to the base station, so you must always estimate this clock bias. This is also the principle that is happening in GPS, where a user must be connected to 4 GPS satellites in order to localize itself, so to figure out its 3D location and also synchronize itself to the GPS satellites. The way that we do this is typically using wideband waveforms in communication, so OFDM signals where we send pilots over subcarriers at the receiver sites. At each subcarrier we have the transmitted pilot, and then a phase rotation which depends on the delay and the subcarrier index, so the phase grows linearly over the subcarriers. And then using FFT processing, we can look for peaks, and this immediately gives us the delay, so that provides a quick and easy estimate of tau and also a way to detect multiple targets. So this is very common, also used in radar. In addition to this, you can also have angle measurements, for instance, angle of arrival and angle of departure measurements. So the figure on the left shows a base station here with an array, a remote user, which is sending a signal. The signal arrives at the array, and then by measuring the electric field across the antenna elements, you have this kind of observation model. And then you can use standard array processing techniques to estimate this angle of arrival, for instance, FFT or music or whatever is your favorite tool. And then this provides you with this angle of arrival theta. And then the base station knows that the user is along this direction, and this provides very useful information for positioning. You can also do the converse, which is angle of departure estimation, a little bit less intuitive. So again, you have the base station here sending a signal towards the user, and if the user has only a single antenna element, this would be the observation model. So the received signal would be the base station steering vector times the transmitted waveform plus noise. And then you can convert this to discrete time observations. And from this discrete time scalar observation, the user, by collecting information across time, can figure out this angle theta. So you can figure out this angle of departure from the base station to the user. And the most standard way that this is done right now is that the base station would generate directional beams in different directions, and then the user would collect the waveform, for instance, measure the signal strength, and then the direction corresponding to the largest signal strength would be declared as the angle of departure. So these are the I guess, three most common measurements: delay, angle of arrival, and angle of departure. And then you can put them together in different ways. So you can do pure delay-based positioning. So if you have 3 base stations in a 2D environment, you can compute 2 time difference of arrival measurements. A little bit more about that later. And then you can find yourself on the intersection of 2 hyperbola. On the other hand, you could, for instance, use only angle-based measurements. So if you have angle of departure measurements from 3 base stations, you can localize yourself based on the intersection of directions, and any combination of the above. So here you have 3 base stations where 2 provide a time difference of arrival measurement, so hyperbola, and 1 base station provides a directional measurement, so a line, and the intersection of this line and a hyperbola. That's where you are. The figure on the top right shows what would happen if the base stations and the users are perfectly synchronized. In this case, the time of arrival measurements can be directly mapped to distance, and then you're on the intersection of 3 circles. And yeah, many people work with this kind of measurement, but that's not what really happens in practice because of this clock bias. So in practice, you would have this hyperbola. And a meaningful question to ask then is, how many base stations do you need to solve the positioning problem? So for instance, in the first problem with time difference of arrival, you need 3 base stations to localize yourself because you have a 2D position, a 1D clock bias, so you have 3 geometric unknowns, and you have 3 geometric measurements, the 3 time of arrival measurements. All right, so how does this then map into what's happening currently in 5G? So this is the typical 5G way of positioning using time difference of arrival. A user, in this case an uplink, is broadcasting a signal. The signal arrives at different base stations. These base stations are perfectly synchronized, or they're time synchronized. Each base station measures the arrival time of the signal, so it has an estimate which we call tau hat I. So the arrival time of the signal at base station I is the distance between the user and the ith base station over the speed of light plus the clock bias plus noise. And then to get rid of the clock bias, we compute these differential measurements, which we call yi. In this case, base station 0 is the reference base station, and the other ones are then used to compute the time difference of arrival measurements. So with 3 base stations, you can compute 2 time difference of arrival measurements, and each time difference of arrival measurements determines a hyperbola, right? Because the differences of distances should be constant. This is what's shown in the figure on the right. So there are these 3 base stations. The user measures time difference of arrival, so you have 2 time difference of arrival measurements. And then you see that the user must be localized on the intersection of those hyperbola. Now, these are not perfectly geometric hyperbolas. They are somehow blurry, and they are blurry because of multipath effects. They are blurry because of measurement noise, and also they are blurry because of the geometry that is considered. The performance is limited by a number of factors. So first of all, where the base stations are. If all the base stations were on a line, that would be very poor geometry. This is also what you see in GPS. So if you're in a city and you only have satellites above you, you will not be well localized. It is also limited by the number of base stations that you have available. So you need 3 base stations to localize yourself in 2D. And this is really something that's very different from communication, where in principle, if you're connected to 1 base station, you are connected to the system. And as I said, you're limited by bandwidth and multipath. So going a little bit deeper into what limits the performance, we can think about what limits the performance at the link level. So how well can we estimate, for instance, delays or angles, and what limits the performance at a system level, so in terms of really the positioning performance. So at the link level, there's different factors. The first one is, of course, measurement noise, so you're limited by SNR. And this you can improve by just boosting your transmission power, or longer integration times. And again, this is something different from communication, where you want to send a packet of data within a coherence interval. Here you can deal with much longer coherent intervals, for instance, by including the Doppler, and also because of the fact that you're only sending pilots. A second factor that limits performance at the link level is multipath. So when you have different paths arriving more or less at the same time as the line of sight path, this leads to performance degradations. The only way to mitigate that is by having higher resolution. For instance, by having more bandwidth, because more bandwidth allows you to separate the multipath over time. You could also have higher resolution angle, which allows you to separate multipath in the angular domain. And finally, there's a limited accuracy of the measurements, and this can be then boosted by, again, more power or longer integration times, but also by optimizing the waveforms. So this is really related to also the previous talk. You could optimize the waveforms a lot if you know something about the environment, and that way you can boost your, for instance, time of arrival estimation performance. There's also factors at the system level. So for the positioning itself, blockage of paths. So a certain base station may be blocked from a certain location. This you can mitigate by having more base stations. Limited accuracy. This again, you can have by having more base stations available and also place them in a correct way. And then finally, an issue that may occur is that you have infeasibility if you only connect to 1 or 2 base stations. And again, the solution is a higher number of base stations and optimized placement. So it seems at a system level, the way that you boost performance is just by putting more and more and more base stations. But it's not really desirable because this leads to higher energy consumption. There's also considerations regarding privacy and so forth. So maybe there's alternative techniques that we can consider for improving the system level performance without needing more base stations. And for that, intelligent surfaces are a potential technology. So reconfigurable intelligent surfaces are one of the envisioned key technologies towards 6G. So this is a slide that I usually give when I talk about localization. So there's a number of factors that contribute to high accuracy localization in 6G. So one of them is having higher carriers, another one is having larger bandwidth, more antenna elements for higher resolution, the presence of side link, network densification, so having more base stations, integration of sensing, localization, and communication, so having localization help communication and vice versa, the more widespread use of artificial intelligence to solve certain hard problems, and then shaping the environment with intelligent surfaces. And I'm happy to spend 1 hour on each of these 8 topics and also on the challenges, which are the hardware impairments and the calibration. But for today, I will focus on this 8th bullet, which is to shape the environment with intelligent surfaces. So just to provide a common background, so what are these intelligent surfaces and how do they work? So this is a figure I took from this highly cited paper by Bassar and Di Renzo from IEEE Access from a few years ago. So this is the canonical scenario. You have a base station here on the left, there's a number of users on the right, and the line of sight between the base station and the users may be blocked. And as you know, when you go to high carrier frequencies, the line of sight path is the one that you really want to use for communication. So when it's blocked, all of a sudden you're in a very low SNR scenario, and this is where these intelligent surfaces come in. So there's an intelligent surface here, which is essentially a reflect array, you can think of it like that, which is reconfigurable. Okay, so it has controllable phases in this case. So each of the elements has a controllable phase, and this controllable phase you can then set to provide maximum end-to-end SNR. And the main benefit of intelligent surfaces is, and this is a quote from that paper, they are nearly passive. Ideally, they don't need a dedicated energy source. So you put them on the wall, maybe you need a small battery just to do the control and also to communicate with the outside world. But other than that, it's a passive entity. So it's really something green that you can use to improve communication. Let's look at the signal model just to provide a little bit more mathematical details. So if you have these K users, they each have a single antenna. So at a specific user, you would have this kind of observation. X is the transmit signal to base station. HBR is the MIMO channel between the base station and the RIS. Omega is the RIS control, so the RIS configuration. And HRU is the channel, which is this is a row vector between the RIS and the user. And then you can optimize this omega to maximize the overall SNR. And then in case the line of sight path is there, you can just add it to the observation model and it will be present as well. Now, for communication, when the line of sight path is present, the RIS does not add very much. Right? So it's a kind of incremental improvement to the SNR. But for positioning, actually, both of the paths are very useful. So when we look at RIS for localization, I have here the same channel model, right, the same observation model, but I look now in more detail, how do each of the channels look like from a geometric point of view? So if I look at the channel HBR between the base station and the RIS, I can express it like this, right? So there's a steering vector at the base station, which depends on an angle of departure. There's a certain channel gain between the base station and the RIS, which depends on the path loss and antenna element gain effects. And then there's a response vector at the RIS, which depends on the angle of arrival at the RIS. So this channel, HBR, is in this case a rank 1 channel between the base station and the RIS, considering pure line of sight. So I remove all the multipath here just to focus on the geometric channel. Then there's the RIS configuration omega, and then there's a channel from the RIS to the user, which is again a channel gain, the RIS response factor as a function of the angle of departure. And the reason I decompose it like that is because from a positioning point of view, I really care about those angles here, the angle of departure and angle of arrival. And in principle, if I know where the RIS is and I know where the base station is, the angle of departure from the base station to the RIS is known. Right? Similarly, the angle of arrival from the RIS towards the base station is also known. So the only thing that's unknown is this angle of departure from the RIS to the user. And if I can estimate this, I can localize the user to be on the line, even when the line of sight is blocked. The downside, of course, is that I have to multiply those two channel gains, alpha BR, alpha RU, both subject to path loss, so overall the channel gain will be really low. And this is, of course, where the RIS phase configuration comes into play to kind of mitigate this and boost this SNR. Okay, and for those of you who are interested, we wrote a magazine paper, which is now 2 years old, on a kind of vision of radio localization sensing with RIS, where you can find much more details about this. Here I just provide a more high-level overview. Okay, this is the same. All right, so there are different flavors of RIS. The one that's more common is the one here on the top in the middle, which is the so-called reflective RIS. So there's a source emitting a signal. The signal bounces off the RIS. The RIS controls it through its phase configuration to go in a certain direction, for instance, here towards a user. But this is not the only function. There's also a hybrid RIS. So in this case, the signal can partially reflect, but also partially go through the RIS. And then there could be an RF chain at the RIS side, which could collect information and then also help channel estimation in principle for communication, but also help estimating angles and delays for localization. And then on the right side is also another extreme where the RIS operates as a lens. So the signal goes from the base station here to the RIS, and the RIS can focus the signal to the other side, and there can then be an antenna with an RF chain, and you can process the signal there. And these are the kind of standard versions of RIS, where again the reflective RIS is the one that is most common, but all of these versions are kind of research fields by themselves. For each of these, we can consider also different operating regimes. So the first one is the near field regime. So where the base station and/or the user are in the geometric near field of the RIS. This means that with each of the different propagation paths, there's in principle a different path loss, different angles of arrival, angles of departure, and different delays. So this happens when the user is close to the RIS. And in this case, the received signal is a function of the user location, which is unknown, the RIS position, and the base station position, and the last two are known. In the near field, you can do cool things. So you could configure the RIS phase profiles to boost energy not towards the direction of the user, but towards the location of the user by exploiting the wavefront curvature. And then this allows you to estimate the user location, exploiting wavefront curvature, even when the line of sight between the base station and the user is blocked. So a more common model is the one on the right, which is the far field model. So where there's one common angle of arrival, angle of departure for all of the propagation paths. All of the paths have the same gain, so there's only a phase difference between the paths. In this case, the received signal is a function of angle of departure and angle of arrival. Okay, angle of arrival is known because the base station and the RIS have known location, angle of departure is not, and the delays. In this case, we can do traditional beamforming towards a certain direction, and then estimate the user from the estimated angles and delays. In this case, you cannot localize the user when the line of sight is blocked. You just don't have enough information. You just have the two angles of departure, which constrains the user to lie on a line away from the RIS, but that's not enough to localize it without ambiguity. All right, so this provides some background. So now let's think about how can we use this RIS for solving really hard localization problems. So the conventional 5G thinking is that to do localization, you need several base stations, right? And each of those base stations needs a power source. And also all the base stations need to be very finely synchronized. And when I talk about fine synchronization, I mean nanosecond level. The reason is that a small error of, let's say, 1 nanosecond leads to a distance estimation error of 30 centimeters. So if you want meter level accuracy, you need to have nanosecond or sub-nanosecond inter-base station synchronization. So this is the conventional 5G thinking. When we think about what could happen in 6G, we can use RIS, and we see here that RIS is a green technology in the sense that it doesn't need dedicated power sources, it doesn't amplify the signal, and the question is, can it then be used to reduce the number of base stations? So our research question in this talk is, what is the minimum number of base stations plus RIS needed to localize a user? So when there's no RIS, we know these answers. So we've seen that in 2D, you need 3 base stations to localize yourself with TDOA. What happens when we add RIS into the mix? Now, to answer these questions, we need to make certain assumptions. And some of these are questionable, some are not. So the first one is that each RIS has a known position and a known orientation. This seems a very natural assumption, but in practice, this may be very hard to meet, right? Because maybe RIS are put up by a regular person in their house, they will not know what is the exact position orientation. In particular, knowing the orientation is very critical, because if the orientation, like the tilt of the RIS, is maybe 1 degree off, that means that angle measurements will be useless when the user is far away from the RIS. We also assume that each RIS has a local controller, which we call a RISC, and that local control is connected to the network. So that allows the RIS to control and to act based on the current situation. And finally, we assume that, well, and this is a reasonable assumption, that the user and the network are not perfectly synchronized. So the user has a clock bias with respect to the base stations and the infrastructure. And then to answer this question, we break up the scenarios into 4 different cases. So these are really natural. So we first will look at SISO, so where base stations and user each have a single antenna element. Then SIMO, where the base station has a single antenna element and the user has multiple antenna elements. MISO with a multi-antenna base station, single antenna user, and finally the more general MIMO scenario. And as you can imagine, when we go from SISO to MIMO, the requirements on the number of base stations will be reduced because we have more measurements per base station or per RIS. Okay, so I will go through the SISO case in some detail, and then SIMO, MISO, and MIMO I will go really fast. So first of all, the SISO case. Let's look at the left column here. This is the case where we don't have any RIS, and we want to localize ourselves in 3D. And then there are 2 cases, the wideband and the narrowband case. So here by wideband, I mean that we have an OFDM signal where we can estimate delays of different multipath components. In the narrowband case, there's only 1 subcarrier, so I can only have angular information. So we see that in wideband, we can localize the user when we have 4 connected base stations, which are all mutually synchronized. This is because the 4 base stations provide us 4 time of arrival measurements, which provide us 3 time difference of arrival measurements, which is needed to localize the user. Right, so the user will be on the intersection of 3 hyperboloids. Let's see what happens when we add 1 RIS. So when we add 1 RIS, then we have the potential to localize the user with a single base station. So let's say that the base station is broadcasting a signal in downlink. There's a direct line of sight path from the base station to the user. And then there's a path from the base station to the RIS to the user. Each of these paths has a certain delay, in this case tau 1 and tau 2. And the path from the RIS has a certain angle of departure, which is denoted here as phi 1. And this angle of departure has 2 components, because it has an elevation and an azimuth component. So you see that in principle you have 4 measurements, right? 2 delays and 2 angles, azimuth and elevation. So you have 4 geometric observations. You have 4 unknowns, the 3D position and the 1D clock bias. So there's potential that you can localize the user this way. And we will see in a few slides that this is really possible. There's an even more extreme version of this where you have 1 RIS and 0 base stations. So in this case, the user needs to be operating in full duplex mode. So the user is emitting a signal. The signal bounces off the RIS and goes back to the user. And from the round trip time, the user can estimate the delay. And if the user can estimate also the angle of departure from the RIS to the user, it can also localize itself on a line away from the RIS. And this intersection of a line and a sphere gives a 3D position. So this is in principle also possible. I will not talk about this today, but you can find more in our ICC paper, which we will present next week in South Korea. In case you have narrowband transmission, so only a single subcarrier, even with a single RIS, you cannot solve the problem. When you have two RIS, on the other hand, of course, in wideband, you can solve the problem. If you can solve it with one RIS and one base station, you can also solve it with two RIS and one base station. In narrowband, in this case, also you can solve the problem. So in this case, you have one base station, one user, both of them with single antenna and two RIS. The base station is illuminating the two RIS, and then by clever configuration of the RIS phases, you can estimate the angle of departure from the first RIS to the user and the angle of departure from the second RIS to the user. And this constrains the user to lie on the intersection of two lines, which is a unique point, so you can localize yourself. And in fact, I see this kind of approach on the bottom right as the easiest way to use RIS for localization, just based on angles. No fine synchronization is needed. You just need to be able to generate directional beams at each of the RIS and have some kind of orthogonality between the two RIS. Okay, now the first time you see this maybe sounds a bit strange, so let's go into a little bit more detail in this case scenario with one RIS, one base station, half duplex. So what is really going on and how does this work? All right, so now we go in a little bit of math. I hope you're all awake and had some tea or coffee. So we consider downlink transmission from the base station here towards the user and the RIS with TOFDM symbols over n subcarriers. The base station has a known position PB, the RIS has a known position PR and a known orientation, which is given by these three unit length vectors. And the user has an unknown clock bias and an unknown position. And we want to localize the user. And note here that I don't put any multipath, I don't put anything in the environment. It is possible to also include multipath, and in the paper cited below, we investigated to what extent multipath harms the positioning, but I want to focus here on the core problem, localizing with a single RIS. So the signal observed at the user, you can write it as a matrix, right? Because you have observations across subcarriers, and then you have T transmit OFDM symbols, you have a matrix of observations. And then we have here two paths, the line of sight path with a complex channel gain alpha line of sight. We have here D of tau B, which is just the increase of the phase across the subcarriers induced by the delay tau B, which we've seen earlier, just the standard OFDM impact of delay. And here I write as 1 of T, which just means that on each of the subcarriers, on each of the OFDM symbols, I just send unit norm pilot 1. Okay, I can put whatever I want there, but this is just to make the math easier. And then there's the path from the from the base station to the RIS to the user, alpha RIS. So this is typically a very small number compared to the line of sight gain. And then here I have a component across the subcarriers. So a linear increase in phase depending on the total time of arrival. This includes the time from base station to RIS and RIS to user. And then across the time index, I have this steering vector U of depending on the angle of departure theta. Okay, and this is again the standard form that we've seen before of how the RIS operates, right? So from the point of view of the RIS, there's a signal coming in with a certain angle of arrival here. It is then modified by the RIS phase control. So this is a diagonal matrix that tells how the RIS is controlled. And then the signal is again with a steering vector with an angle of departure. But overall, this is a scalar because from the point of view of the base station, it looks like a single path, a single antenna channel. And then the steering vector is written here explicitly, so it depends on the relative position of the RIS elements and a unit vector from the RIS to the user or to the base station. This is a standard model. All right, so let's see what is known here. So the two complex channel gains are unknown. Tau B is unknown. Tau R is also unknown. The angle of arrival at the RIS is known because we know the relative geometry of the RIS and the base station. The angle of departure is unknown. And then this omega t is also known. These are the RIS phase profiles that we designed to have optimized performance. All right, so then we try to now localize the user with this information. And again, as I said, in principle, it can be done because we have 4 geometric observables, 2 delays, 2 angles, angle of arrival, angle of departure and azimuth elevation, and 4 unknowns, the position and the clock bias. So just here to make sure we're all on the same page. So the delay of the line of sight path is the distance over the speed of light plus the clock bias, and the delay of the path via the RIS is the distance from the RIS to the base station over the speed of light, the distance from the user to the RIS over the speed of light, plus the same clock bias. All right, so this is our observation model. So one of the tricks that you can do with RIS is you can optimize the RIS phase profiles to separate the line of sight path and the RIS path. Right? And this is called temporally balanced profiles. And if you do that, you can separate the line of sight path from the RIS path, and then the RIS path is gone. And this then you only have a single path available here, and to estimate the parameters of a single path, you can just do a single FFT. So you take this observation, which is just an observation across the subcarriers, compute an FFT, and then you get the delay and the line of sight channel gain. If you don't want to use these temporary balanced phase profiles, you could use random phase profiles for this U here, and then add everything up across the OFDM symbols, and then approximately the second equation will hold. So the RIS path will be kind of averaged out and close to 0. You only have the line of sight path plus noise. Once you've estimated the line of sight path components, you can subtract it from the original observation, and then you have only the path from the RIS left over. And now you could do an FFT again to estimate the delay, and then you can do a 2D search to estimate the angle of departure from the RIS to the user. So it involves a few inner optimization problems. The largest one is a 2D search over the angle of departure. So you can do this rather quickly. So then you're given the two delays, right? The line of sight delay tau b, the delay of the RIS path tau r, and the angle of departure from the RIS to the user. So what you do then is from the two delays, you can subtract them, and this gives you a hyperbola, or in 3D, a hyperboloid. It's a time difference of arrival measurement, right, which depends on the position of the base station and the position of the RIS. So this limits your location to lie on this hyperboloid. And then from the angle of departure, you can draw a line away from the RIS, which constrains your position. So you're somewhere on this green line determined by the angle of departure. And then the intersection of the two, in principle, gives you your position. And once you've found the position, you can use the line of sight delay to figure out your clock bias. And then automatically you are synchronized to the base station. Now, of course, the measurements are affected by noise. This hyperboloid will not exactly intersect with the user. The angle of departure is itself uncertain, so there's basically a cone rather than a line away from the RIS. But still, you can localize pretty well. So what we're shown here on the right is as a function of the distance from the RIS, as a function of the distance between RIS and user, so here from 1 meter to 10 meter approximately, the error in the different dimensions. So we have the error on the clock bias and the error on the position. And the yellow markers here are the estimated position, or the errors of the estimated position, and the yellow line is the corresponding Krimeriow bound. So that tells us what is the best that we can do. And we see even with this very simple estimator, we get very close to the Krimeriow bound. When you get further away from the RIS, of course, the performance degrades just because of the path loss effect, right? You have both the path loss effect and also the effect that a small error in the angle of departure will lead to a huge error in the position when you're far away. So you should be relatively close to the RIS for this to be useful. The figure on the top right shows the quality of the delay estimation as a function of distance. So we have the line of sight delay and the RIS path delay, and you see that you can estimate, in this case, the line of sight delay really, really well, while the RIS delay is much worse. And again, this is an effect of path loss. This is because the line of sight path loss is much, much less than the RIS path loss, because you have to go these two paths. And then here on the right, bottom right, we show the impact on the number of RIS elements as a function of the position error bound. So how well we can localize for a different number of RIS elements. And you see this kind of linear decrease in the log scale. So it's really beneficial to have more and more RIS elements to do the positioning. And in this case, the phase control of the RIS was not optimized in any way. We didn't assume a priori we knew anything. We just randomly set the RIS configuration. So it's not even beaming in any direction. And still you can localize really, really well. So that means that you can bring down this positioning error even an order of magnitude better by having better RIS profiles. If you know something about where the use is more or less, you can further design the RIS profiles and then bring the error even further down. All right, so I hope this gives you some intuition that even with a single base station, just by putting a RIS on the wall and knowing where it is, all of a sudden you unlock this very hard localization problem. If the RIS was not there, you know nothing, right? If the RIS was not there, all you had was the line of sight delay, okay? And okay, if you knew the clock bias, that would put you on a sphere around the base station, still not informative, but since you don't even know the clock bias, you're basically on an infinite number of spheres around the base station. So you know very little of where you are. And then by putting the RIS, all of a sudden, tada, you are localized. All right, so this is was the kind of the hardest case, the CISO case. The next two cases are a little bit easier. So the first one here is now the MISO case, where the base station has multiple antennas and the user has a single antenna element. When we have zero RIS, we already know how to do that. So this is the same as before. When we have narrowband communication without any RIS, so only using base stations, we need two base stations, right? We need two base stations because from the first base station, we can compute the angle of departure. From the second base station, we can compute the angle of departure. And this gives us two lines, and the intersection of those two lines tells us where we are. If we put the same scenario in the wideband case, that we also have one time difference of arrival measurements, so then we can even further improve our positioning quality. If we now consider the case with one RIS at the bottom here in the narrowband case, so a multi-antenna base station, single antenna user, and a RIS, then we see that in principle we can estimate the angle from the base station to the user and also the angle of departure from the RIS to the user. And then we have those two angles, and again this puts us in the intersection of two lines and we can localize ourselves. So recall in the CISO case we could not localize ourselves with narrowband signals, but now with the help of RIS in the MISO case we can localize ourselves. Now the quality of the localization really depends on the size of the base station, the size of the RIS. So if you have a base station with just a few elements in both dimensions, your angle estimate will probably not be very good, especially when you have multipath to deal with. So my advice typically is that if you want to do localization, time-based measurements are really, really valuable, probably much more so than angle-based measurements. Right, the next case is the SIMO case, which is a bit weird case, right? Because now the base station has one antenna and the user has many antenna elements. So maybe not the most conventional case, but you can anyway try to figure out how to solve it. So in this case, you have three base stations, each with a single antenna element, and then a user with, let's say, a planar array. And then the user can estimate angles of arrival, theta 1, theta 2, theta 3, in azimuth and elevation. And then you can show, and this requires a little bit of math, that you can localize the user in 3D and also figure out the orientation of the user in 3D with three base stations. And if you just think about the counting argument, so the 3D position and the 3D orientation gives you 6 unknowns, and then the 3 angles gives you 6 observables, right? Because each angle has an azimuth and elevation. So from a counting argument, it's plausible that you can solve this localization problem, but you can actually really show mathematically that this localization problem is solvable. This is how you would do SIMO localization without any RIS. Now, when you add a RIS, things become easier. So you have a single base station now, a RIS and a user. The base station has only one antenna element. The RIS, of course, has many elements. And now let's see which angles we can estimate. So we can estimate the angle theta 1 from the RIS. So that's an angle of arrival in azimuth and elevation. The angle theta 2 from the base station in azimuth and elevation. And then the angle of departure from the RIS to the user. Here we can estimate as well. So let's see how many observables we have then. We have theta 1 and theta 2 is each 2 observables. Phi 1 is also 2 observables. So we have 6 observables, 6 unknowns. So it is plausible that we can localize ourselves. So, and notice that in contrast to the previous cases, now I need to include the orientation, right? In all the previous cases, I had a single antenna user, and the single antenna user has no orientation, right? It cannot measure any angles. But once I have an array at the user side, orientation becomes important. If I change the orientation of the user while keeping the position fixed, all the angles will change. So for all the angles of arrival to make sense, I need to either know the orientation or estimate the orientation. So here we consider the case where we estimate the orientation. Then the last case is the MIMO case. This is somehow the easiest case. So let's look again at the narrowband solution. So if we have 2 base stations with several antennas, a user with an array, then in this case we have 8 measurements, right? We have all the angle of departure measurements from the 2 base stations that determines the location of the user. And then the angle of arrival measurements from the 2 base stations tells you the orientation of the user. So we even have too many observables compared to the unknowns. We have 6 unknowns and we have 8 observables. So even we have too much information. When we add a RIS, again, the scenario is the same. We put 1 RIS and 1 base station. Again, we have 8 angles that we can measure in azimuth and elevation. We have only 6 unknowns. So again, the problem is solvable. So you see that in all of these cases, you can really significantly reduce the number of base stations needed just by putting a RIS with a small controller, small battery, and really enable this green localization. Now, sometimes I get the question, which is better? Should I use the base station or is it better to put a RIS? And the answer is not very straightforward. So if you look at these two scenarios, scenario A and B, this is for the MISO case, so multi-antenna base station single antenna user. So I can either have two base stations and I measure the angles of departure, or one base station and two RIS and I measure those angles of departure. Which one is better? So if I think just about cost and energy consumption, definitely the one on the right is better, right? Because I only need a single base station, single power source, and I don't need to do perfect synchronization of the RIS here. While scenario A, I need two power sources, maybe the base station needs to be time synchronized, you need to have a GPS receiver and so forth. So this is much more power hungry. Then let's think in terms of accuracy. So if I just think about pure received SNR, scenario A is definitely better because I have this single path loss, while in scenario B, I have the path loss from base station to RIS and RIS to user. So the SNR will be much lower, which you need to mitigate by having either higher transmit power or longer integration times. If I think about angle resolution, so how narrow can I make the beams, then probably scenario B is better because it is typically easier to have a RIS with many, many hundreds of elements compared to a base station with many hundreds of elements. So it is not really clear which one is better. And I think it depends on the specific deployment scenario, which one you would choose. All right, so this was kind of a sampling in our paper, which is this one here, leveraging RIS-enabled smart signal propagation for solving infeasible localization problems, which you can find on arXiv. We go through all of the scenarios in detail, considering narrow band and wide band, different kind of measurements. And in some cases, we can also we can estimate both the position, the clock bias and orientation, but in some cases, we can even estimate the velocity, right? So by having Doppler measurements, you can reconstruct the 3D velocity from the measurements. And then there's many variations of this with near field, with other kind of propagation effects, which I don't cover. All right, so this was kind of just a sampling of what is possible with RIS in terms of solving the hardest possible localization problems. We found that RIS leads to many interesting and unexplored research problems. We're always continuously surprised by using RIS. There's a big problem, which is that we don't have very good models of RIS channels, including their hardware impairments. An important challenge is also the design of good RIS configurations, right? And here there's a big difference between communication and localization. If you want to do localization, you should just beam as much energy towards user as possible. If you want to do localization, that's actually a very bad solution. You should send different kinds of beams at different times. We should be able to support multi-user, multi-RIS, and multi-operators for localization sensing. We also should have good models under near-field propagation and also non-stationary extra-large MIMO regimes. An important challenge is also calibration, so we need to figure out where the RIS is, what is the orientation with very high accuracy, and finally practical demonstration. And to this end, we actually did a small demonstration at Chalmers with our colleagues from the microelectronics laboratory, where we considered two RIS and one base station, sorry, this was one base station, so it's actually not this scenario, I will show the scenario here. So we have one base station here emitting a source signal, two RIS, which are basically two transceivers where we feed back directly the receive signal to the transmit signal. We use directional beams, and then we want to estimate at the user side the angle of departure through these directional beams. So we know perfectly where the RISs are, we know where the base station is, but we don't know where the users are. And then by using these directional beams, we can localize the user based on the received signal strength. So here, this is a very small scale environment. I mean, the distance are only a few meters, but we can localize the user just based on angle measurement with a very small uncertainty. All right, so one thing I didn't talk about is what about RIS for sensing? So everything here was about localization, how to localize a user with RIS. And when we think about RIS for sensing, I think we should be a bit careful and maybe also a bit realistic. So thinking about the path loss equation, which we use in communication and also in localization, and the radar equation, which is used in sensing, there's an important scaling that we should take into account. So when we have a transmitter transmitting with some power and a receiver some distance away, the received power scales like this, right? So it's a transmit power times lambda squared over the distance squared. So it's proportional 1 over the distance between transmitter and receiver. When we do radar, monostatic radar, the received power scales with the distance squared between the transmitter and the target and the distance squared between the target and the receiver. So it scales as d to the power 4. Right? So the received power from a radar signal is much, much weaker than from a communication signal, given the same transmit power. All right, so with this in mind, let's look at this scenario where we would use a RIS for sensing. So there's a monostatic radar here emitting a waveform, a target here, and the red path is the common radar path, right? And now we put a RIS, and we could have a path from the radar to the RIS to the target, back to the RIS to the radar, or a path from the radar to the RIS to the target, and then directly to the radar back. So the radar path, so the path from radar to target back to radar, has d to the power 4 path loss, already very weak. When we think about the path A, B, C, right, which is a reasonable path, including a RIS, we will have d to the power 6 path loss. And also we need to associate measurements among the path from the RIS and the direct path. And then the path A, B, D, E, actually I made a typo, it's d to the power 8 path loss, not d to the power 6. So these paths will be incredibly weak. So you really need to design the RIS phase profiles in a very smart way to overcome this high path loss. And while there's some research going on RIS for sensing, I think we should be very careful and consider the path loss in a realistic way and make sure that it does not become a killer for radar sensing with RIS. All right, this leads me to the end of the presentation. So this is more the vision of what I see 6G will be. It will have communication, radar, sensing, other kind of sensing as well, AI, more bandwidth, more antennas, localization, and the focus of this talk, adaptive environments. And all of this together will be the 6G system, which will lead to new possibilities, new applications, new use cases, new requirements as well, and a lot of challenges that we must face. So this brings me to the final slide. I hope that you're convinced that radio signals are good for localization. The regime with high frequencies, large bandwidth, and many antennas, where we're going towards in 5G and 6G, is really promising. In 5G already you can do single anchor positioning, synchronization mapping, and 5G in principle could be a low resolution radar. But when we think about sensing and localization, beyond 5G is really where things will happen. RIS will boost and enable localization problems. We will have flexible requirements which require adaptive signals and methods, including for RIS. We foresee a convergence of communication and radar processing, for instance, that automotive radar will be replaced by a 6G radio. Hardware limitations, which I only touched upon, but they will be a big problem, I think, in future communication systems. And I think it's important that we learn from our connected fields, such as from GNSS, from functional safety, and synthetic aperture, to really exploit the 6G system as much as we can, including for RIS. And I think it's a really promising and exciting time to work on radio-based positioning and sensing. And I think the golden age for us has just begun. And this brings me to the end of my talk. Thank you.
Thank you, Professor Henk, for this nice presentation. Now the floor is open for questions. Yeah, go ahead, Professor Wissam.
Thank you very much, Professor Henk. I have a question regarding the RIS with multiple frequencies using OFDM with RIS. I was wondering, according to my understanding, that we can control the delay that the RIS causes to the incident signal, not the phase, which means that if we control the delay of a certain element of the RIS, this means that the phase of frequency F1 will be different from the phase frequency F2, which means that different frequencies will be reflected at different directions. So how can we interpret this in terms of your work here? Because in work you assume that all the frequencies will have the same reflection direction or the same phase exactly.
Yes. So this was a simplification. You're completely right. So in practice, each of these will be a delay and then measured at a certain frequency that corresponds to a phase. That's true. So when you have an extremely wideband signal, then you will have variations of the phase control across frequency. However, I think the system that we are considering here are maybe a few hundred megahertz in bandwidth, in which the approximation of having a phase is still relatively reasonable. But yeah, I fully agree that the correct model is to have a delay which then transits to a phase which is varying across frequencies.
Thank you very much. Thank you.
Okay. Any other question, please? Professor Henk, I have a question, just not a question, a clarification about the far field and the reflective RIS. Aren't they the same?
Well, the reflective RIS, as shown here, I mean, you could be close or far away from that RIS. If you're very far away from the RIS, you will be in the far field, meaning the flat wave propagation regime. But if you're very close to the RIS, you will see the wavefront curvature. So I think both combinations are in principle possible.
Okay.
No,
Yeah, Ali Muhammadi. Go ahead, Ali Muhammadi.
Hello, I got a question.
Yeah.
It seems that localization, Assalamu alaikum. It seems that localization can be used in what they call houses or rooms. What about if we use it in clusters, I mean, outdoor for streets? Is that possible to use a RIS? Where are we gonna, install it?
Yeah, in our experience,
Station or?
yeah, I think it should be in a kind of maybe dense urban area where you care about precise localization, where it otherwise would be very hard.
Is it possible to use in highways? I mean, like cities, clusters, nearby,
Okay.
station users.
I don't think that there's a need for have it in highway, because for a localization perspective, you could just use GPS. So we see this 5G, beyond 5G localization really in indoor environments and very challenging urban environments. And there is also where they envision RIS to play a role, because there could be a blockage of the line of sight, you put the RIS, and then the blockage is resolved by aid of the RIS. And then we can reuse the RIS for localization.
So it should be only for indoor houses.
Indoor and urban outdoor environments, but not in highways or rural environments. I don't see any use case for that there.
Oh, possible in the street. I mean, like, in the clusters.
Yeah, in a street in a city, yes.
I see. Thanks.
Any other question, please?
Dr. Azadin, if you allow me.
Yeah, go ahead.
Again, thank you, Professor Henk, for the presentation, and thanks for accepting the invitation. You mentioned the scenario of radar sensing and RIS. I think we have the case of wireless sensors, where it's not really communication system that use RIS, but rather a sensor with a wireless communication capability. So in that case, we have no problem in terms of path loss.
Okay, so if the RIS itself would be able to sense.
No, I mean, if the sensor itself is equipped with a wireless transmitter. So it's not a radar sensing. So like you have, the other car would itself have a sensor with a wireless capability.
Yes, okay. Yeah, that's a different scenario than this one.
Yeah. It's like a communication, it becomes like.
Yes.
Any other questions? Yes. Reza, go ahead.
Thanks, Professor Henk, for your presentation. I have a question about estimation tau in RIS-aided localization. For example, assume that we have a sparse spectrum, and that means that we have a frequency in a band 100 megahertz, or there is a gap, and then we have a frequency above gigahertz. Can we estimate tau with this system?
Yes, but you will have ambiguity. So if you don't have a continuous spectrum and you take an FFT, you will see a peak, a very narrow peak at the true location, but you will also see peaks at other distances. So the same you have when you have like sparse arrays. You have these grading lobes, you have the same phenomenon here in terms of bandwidth. So for that reason, it's usually good to have a large continuous spectrum or a kind of irregular spectrum to avoid these grading lobes and the delay domain.
Thank you.
Thank you.
Professor Henk, I have one question in the sense that how the RIS, how they are they deployed really now, or they are in the process of being deployed?
There are companies where you can buy a RIS, not at millimeter wave, but at lower frequencies. There's a company in France called Greener Wave that is developing RIS and deploying them. So yes, they exist. Whether they will be used for localization sensing, I don't know, but for communication, definitely.
Professor Anas, you can go ahead, ask a question.
Okay, thank you, Professor Azzeddine. Thank you, Professor Henk. I have one comment, please. We all know that the channel estimation in RIS is a big challenge, actually. So I don't know if Professor Henk can comment on this. Will the RIS itself do the channel estimation for the localization, or it can be done by maybe central unit, or I don't know if he can comment on this aspect.
Well, in this work, and I should say, we only do for localization parametric channel estimation. We want to estimate angles and delays within the channel. We don't care about the overall channel impulse response. And the way that we do it here is at the user side. So the RIS is purely passive. The only thing it does, it kind of flashes different configurations. And the user, if it knows those configurations, can use this information to estimate all the angles and delays. So the RIS doesn't do anything in that sense. It just reflects in some predetermined way that is known by the user, and then the user can estimate the whole channel, or at least the parameters of that channel.
These reflections for each reflecting element, or it can be grouped, done per group of reflecting elements?
Yeah, I mean, I don't, in our simulation, we just use random configurations, but yes, I think it can be in groups, it can be kind of subarrays.
Yeah.
I don't know what will be the performance under those conditions.
Yeah. Thank you very much, Professor. Thank you.
Thank you.
Any other question, please, from the audience? Probably have missed other questions. Please. Two people raised their hands and I could not read their names.
I think we are almost on time, Dr. Azzeddine. So
okay.
Thank you.
If there are no questions, then thank you very much, Professor Henk, for your lecture and for your presence with us here, and really appreciate it.
Thank you.
Thank you.
Bye-bye.
Thank you. Bye-bye. Okay.
So, Dr.
Zahid, the floor is for you, for Dr. Ali.
Yes, thank you very much, Dr. Azzeddine. According to our schedule, so we will have a break of 15 minutes, and we will start our second session at 3:15 p.m.
Okay, thank you.
Please don't go away, stay tuned. So try and come back. Thank you.
Well, it's 3:15 now, so I think we can start. Dr. Al-Hassoun.
Yes, thank you.
Yeah, so welcome all. So we will now going to start our second session, session number 2, which is Green Communications and Sensing 2. The chair of this session is Dr. Mohammed Al-Hassoun, and our first speaker is Professor Greg. So Dr. Al-Hassoun, you can take over from here. Thank you.
Okay, thank you, Dr. Zahid. Thank you all for being here. Professor Durgin, if you want to share your slides, please go ahead.
Can you hear me okay?
Yes, we can.
Great. Okay. Here is my presentation. Do you see that okay as well?
Yes, I think we need to actually, your voice is a bit low, if you can raise it up a little bit.
Okay, how about now? Can you hear me okay?
Yes.
Great, great.
So let me just introduce you to the audience. So Professor Durgin, he received his bachelor, master's, and PhD degrees all from Virginia Tech in 96, 98, and 2000. In the fall of 2003, he joined Georgia Tech as professor or assistant professor in the electrical and computer engineering. He's the founder of the Propagation group at Georgia Tech. His group research is spanned different fields: radio location, channel sounding, backscatter radio, RFID, and applied electromagnetic. He's the winner. He received the Best Paper Awards for the for the articles he authored in in the IEEE transaction on communication. This is Stephen Ori's prize. And in 1998, and Microwave Magazine, IEEE Microwave Magazine in 2014, and IEEE RFID Conference in 2016, 2018, and 2019. He's the president-elect for the IEEE Council on RFID. So Professor Durgin, the floor is yours. Please go ahead, and we'll have about 45 minutes of presentation, then 15 minutes of Q&A. So if you have any question, you can raise your hand, or can you type them in the Q&A chat, and I will echo these questions. Thank you all very much.
Well, thank you for the introduction, Professor Alkhateeb, and I just want to thank the entire organizing committee and yourself at King Fahd University of Petroleum and Minerals for this opportunity to speak and for organizing the event. Looking forward to one day meeting in person with everyone. So today's talk that I prepared is about space ambient power. So before I do anything, I think I should define what space ambient power is, and maybe even just what ambient power is. So to do this, I like to work through this exercise. Hopefully you see before you a section of town in our hometown here in Atlanta, where it's early in the morning. This is a section of the city that I used to walk past every day. It's on the edge of Georgia Tech campus, and it looks like just about any other corner of a city here. It's got shops and residences and that sort of thing. But what could we do if we have ambient power? And by ambient power, I mean a low level of guaranteed RF power available for small motes and tags and items to self-power, energize, do sensing, some computation, and communication. And I picked this scene just because you can look at it and think of some interesting ideas that you could do if you had this low-level guaranteed power level. For example, you could put sensors to detect glass breakage on all the low-level storefronts and windows for security. If you had those low-power sensors available, you could also put moisture sensors in all of the trees that you see there. Of course, they're irrigated in Atlanta because most of the surface area is bricked over or covered over with concrete or asphalt, and then you need to be irrigated. I can't tell you how many times I see a busted irrigation line, and you can always tell, even though it's underground, because a whole row of trees dies off on a city block. You can have corrosion sensors in the park benches, weather sensors to detect precipitation. So maybe that app goes off in your phone when the rain cell sweeping over the city is a minute away to you. You can have sensors that look at crowd noise, small photo sensors for each of the lights, the traffic lights and the street lights, to make sure that they're still operating. They need replacement or maintenance. Parking stickers that detect whether there's a car above the street side parking, linked to an app somewhere that tells you where those open parking spaces are. And you can play this game ad infinitum. We probably already mentioned a couple ideas that we could go file patents on and have some fun with. But the point is, there's really hundreds of interesting sensors just in this frame of view that you could actualize if you had an ambient source of power, something other than a battery. Because if you did all of this across all of the thousands of city blocks like this in the Atlanta area, not only would that be prohibitively expensive, but it would also be an ecological catastrophe because you would have so many batteries, even coin cells, that you'd have to send to the landfill every year. So that's what we're talking about when we talk about ambient RF power. And of course, what we'll talk about for the rest of the talk is our proposition is, okay, let's try to provide that power in a way that's green and ecological and more economical than people have talked about in the past. Normally, when people talk about those type of sensors, they're looking at maybe energy scavenging or harvesting, grabbing signals of opportunity from whatever deliberate transmission or ancillary transmission is being sent out. Cell towers, Wi-Fi access points, things like that. The problem with those is that we've shown in the past, the research literature has shown that those are very spotty ways of covering. It's not reliable. Anytime you put terrestrial point sources, as we'll show in a minute, and try to provide power, even if it's a deliberate power network, it's very difficult to efficiently design that type of power provision. So our proposition is, what if we could provide this background level of power in the far field from spaceborne transmissions? And that's what we mean by space ambient power. So we want to talk about the rest of the outline here. How does a space power system work? How much power do we need to form an ambient sensor network? We'll do a link analysis. And we'll say, how does it stack up against a terrestrial wireless power system? So we'll do a little design of a cellular system that might provide the same amount of guaranteed power level. And we'll see how that stacks up. And then we'll talk about the economics of a space ambient power system and draw some interesting conclusions. So please think of lots of questions to ask at the end so we have a good Q&A session. So let's do a little bit of history. Space solar power was kind of dreamed up by a man named Peter Glaser. In the early 70s, he filed a patent on the idea. And this is just as solar cells, semiconductors were really hitting their stride. The idea was to put solar cells to collect power in space and then beam that power down on a microwave link, focusing it to the Earth, where you would put a collector station that you could tie into the grid, for example, and have this sort of green and renewable energy source. Now, it's a little bit more ambitious than space ambient power, which is a much lower level power level that you have to provide. And we'll get into some hard numbers about how those systems differ. But that's the genesis of the idea. And in some ways, space solar power is sort of the big target that we want to go after in electrical engineering, because it is this way to provide power to reduce some other alternate forms of energy. It's gotten interesting in the last few years because the first reference study on space solar power was conducted by NASA in 1978, not too long after Peter Glaser's patent. And part of it was used as a justification for the shuttle program. The idea is we had this expensive reusable launch space vehicle program. One way to justify it is to say, well, one day we might have to put a lot of infrastructure in space to gather energy and focus it down. And of course, the conclusion of that 1978 study was that the physics are sound, but of course, economically, we are probably 3 orders of magnitude away from actually becoming a reality. But of course, a lot has changed since 1978. Back then, if you put a solar cell up that got about 5% efficiency, you were doing really well. Now, we regularly put solar cells in space that have in excess of 40% conversion efficiency from sunlight to DC. So that's exciting. That's an order of magnitude there. And thanks to Elon Musk, who actually found a way to, he's sort of like the Henry Ford of rockets, he found a way to make them a lot cheaper, and we've had huge gains in that area, and he's promising more, of course. And that's another order of magnitude there. So there's been some excitement recently because there's a sense that we are starting to get within striking distance of space solar power in general. And it's not just tying into the grid. There are some other uses of space solar power that we'll talk about at the very end of the talk. But one of the things that I want to propose in this talk is that space ambient power, not only enabling all of these really interesting green sensors and apps, could be a really interesting stepping stone to space solar power, because there's still a couple of really key roadblocks. And space ambient power requires a much less ambitious infrastructure deployment into space. So it seemed as maybe a less risky proving ground for the technology. So, and then at that point at the end, I just want to say that not long after the reference study, there was another study in NASA that looked at using giant mirrors in space to reflect sunlight down to a city area with the intention of saving a lot of power in street lighting, because you could provide some, not daylight, but at least enough ambient light across your city with the proper geostationary Earth orbit mirrors that would allow you to see at night and drive around. And of course, that is effectively, quote unquote, free energy, because you're not having to tap the grid to drive all those lights. And so that, in a way, is probably the system that represents space ambient power. Do that with RF instead of with straight up light. So let's talk about how to design a space-based power satellite. I have a sketch here of the Earth, and over here on the left is the space solar satellite infrastructure. You have to have an aperture that collects sunlight, that's your solar cell, and then another aperture that transmits power back down to Earth. And in this sketch, I've picked just an off latitude, off equator latitude, such as, for example, the city of Atlanta, which is actually about 33 degrees latitude. So geostationary Earth orbit satellite, for example, is not directly overhead. It comes in close to about a 45-50 degree incidence angle. Now, for anyone that has worked with antennas knows, if you want to focus energy at a spot on the surface of the Earth, you need aperture, you need size. The bigger the aperture, the bigger the area of the transmitter, the tighter the focusing. And in fact, there's a fundamental limit to the gain that you can play with this. I think it's one of the only equations in the talk. I always try to get rid of most of the equations and try to do everything with pictures, because that works so much better in a talk environment. But I couldn't help myself. This one fundamental diffraction limit here on the right. That's the diameter of the transmitter. That's the aperture in space that's transmitting the wireless power, the RF energy, multiplied by the diameter of the receiver. And that's, of course, the spot on the ground that's collecting the energy and the power, is on par, and this is if you want to collect the majority of the power, approximately equal to the distance transmitted times the wavelength of radiation. Now, distances of these systems are quite large, especially if you want to go up to geostationary Earth orbit. That means that the receiver site is going to be at least 36,000 kilometers away, which is a tremendous distance to move across. So as a result, most of these systems are proposed to work up in the microwave bands, anywhere from about 2 to 10 gigahertz. Anything below 2 and the wavelength starts to get really large. And we need a small wavelength to keep the product of the transmitter and the receiver aperture down. Anything above 10 gigahertz, and you start to get into atmospheric losses that become significant. Rainfall knocks you out whenever there's a storm. Even cloud level layers start to attenuate significantly, and you'll even get a little bit of gas and water vapor attenuation as you go through the entire atmosphere. So a lot of the systems that you'll see be talking about are in what we call the C band in microwave engineering. That's around 6 gigahertz, because that's a really nice sweet spot for these systems where the wavelength is small and the atmospheric losses are minimal. So how do apertures focus? It's really not that hard. We antenna engineers like to make things a little bit more difficult than they really are. But imagine you had a flat aperture in space here on the left. And this could be a solid aperture or one composed of modules. If you make them composed of modules, they do have to be synchronized in frequency, which means there has to be some ability to communicate information or estimate position across the aperture. But for the sake of argument, let's just start with the idea that there is a flat aperture across there. And you are trying to focus on this green area down here on the surface of the Earth. And of course, that means that each of these components here has a phase as the wave propagates from one part of the aperture down to here. The spot size on the ground is determined by how far you can move from the center point and still get the same geometrical length on here. In other words, the phase change of this one has not gotten so egregiously bad compared to this one, or egregiously different, such that it starts to deconstructively interfere with the total field strength here on the ground. If that happens, then you're spilling out over into the edge, and you'll get a few side lobes of lower level on either side of this green area. But beyond that, most of your power is actually concentrated here on the green spot. Now, technically, you can also do this with a linear arrangement, but it's much less effective. You don't get nearly the tight focusing unless you go up to a ridiculously large or ridiculously high line of transmitters. But I put this in here just to indicate that it is possible to build volumetric arrays that transmit down to the ground. That's the subject of another talk, but we'll start with this for now. As I said, you can break up this aperture into pieces. One thing you can't do, which is very tempting, is to decimate this array. So for example, if you wanted a modular approach, you say, well, what if I broke this up into tiny little spacecrafts along here that were fleet formation flying? In other words, they all stayed together and they transmitted in unison. And there's a lot of advantages to doing it that way. However, if there's space between those apertures, if they're all arranged in the same plane and there's space between those apertures that isn't transmitting, you will actually get substandard focusing. The spot size down here on the ground won't change, but you'll start to dump more and more energy outside into the side lobes in that incidence. And so you need that entire area in order to get the focusing down here. For that reason, microwave power in general tends to be an all or nothing issue. And this is actually one of the really scary things about space solar power, is that if I want to put focus power into a beam on the Earth, I need to build the entire superstructure in space before I can do that. If I only want to build half of it to test it out, not only do I not only have half of the power, if we're linking power to area for this device, but I also only have half of the aperture for focusing that power. So my energy density on the ground is going to be much smaller than a half, probably less than a quarter at that point. And so it's a sort of the irony of space solar power that those last few pieces of aperture that you put into space give you much more gain than the pieces of aperture that you start building on. And here is just maybe a few examples of the three-dimensional sort of approach that I mentioned, there's actually been a lot of reference studies in the literature over the last 40 years. People sort of love to design concepts for space solar power. There's been a lot of really interesting approaches. I put just two of the more interesting three-dimensional approaches here. Up on the left, this kind of helical surface is called Cassiopeia. It was invented by Ian Cash back in 2017. And then another famous one is this space solar power satellite Alpha Mark I. This is Mencken's 2012 reference design, which is kind of a mountain. It's a kind of almost like a Gaussian shape. It points down to the Earth and stays oriented in such a way that it can collect the sunlight. So the next question I want to ask is, what orbits work best for these? And this is always kind of an argument in the community because, as you know, you can put a bunch of satellites into low Earth orbit, and that's really nice. There's not a lot of distance between low Earth orbit and the surface of the Earth compared to geostationary Earth orbit. But of course, the problem is that any satellite only stays in view for 10, 20 minutes as it's flying over a location in low Earth orbit, because of course the velocity has to be so high in order to maintain an orbit that close to the surface of the Earth. So that's a problem. We need a lot of infrastructure to make that sort of provision if we do it at low Earth orbit. In my view, there's even a bigger problem, and that is the fact that space solar power satellites in general have a lot of cross-sectional surface area, which means they are prime candidates for space collision. And as we all know, low Earth orbit is getting very crowded already. And so the idea of putting a bunch of these things, I asked somebody once at the Jet Propulsion Lab over in California, this is, you guys, I know you do space traffic analysis for this kind of stuff. What's the probability that one of these types of satellites would actually intersect and smash into a piece of space debris in low Earth orbit? It says over the course of a 10-year lifetime, the probability is almost 1. So that's a non-starter for these systems. If you go to medium Earth orbit, the orbits become more expensive, and you have the same problem that you still duty cycle the coverage. In medium Earth orbit, the satellite is not traveling as quickly overhead, so it spends a little bit more time, but you would still need multiple satellites to ensure 24/7 coverage if that was your goal. And of course, the real desire is to use geostationary Earth orbit. The problem with that, of course, is that you have to go 36,000 kilometers away from the surface of the Earth in order to put something in rotation-locked orbit on the Earth, which gives a prohibitive amount of distance. The nice thing, of course, is that you only need to build one of those things because it will hang in the sky and beam down and not move either in azimuth or elevation. So if you have, in the case of a power collection station, a rectinifarm that rectifies and dumps this into the power grid, for example, it can be built at one site and you can focus the power onto that. In the case of space ambient power, we can focus it onto a broad city area of interest, and it won't necessarily move. Now, I do want to add one more thing, this idea of a quasi-geostationary Earth orbit. What a lot of people don't realize is that there's a lot of degrees of freedom for designing these things. Unlike a communication satellite, which really does need to be very finely controlled in terms of its position in geostationary Earth orbit. Why? Because we usually use dish antennas with high gain to communicate with them. We need those dish antennas with high gain and very narrow beam width, not just because we need the gain for the communication link, but also we need to reject any co-channel interference from satellites using the same band. So that pencil thin beam is really important We need only 1 or 2 degrees of half power beam width there. And if you have a satellite that's basically drifting to the left or to the right a few degrees, then you can basically drift out of that beam width very easily if you're a communication satellite, and cause all sorts of problems. We don't necessarily have that limitation for a space solar power satellite of any of these types of systems, because we're just blanketing power at a spot on the Earth. There can be plus or minus 5 or even 10 degrees of change in terms of its position in the sky over azimuth and elevation, and it'll still work. It would still behave properly. We would still be able to focus it. So you're not stuck with just a geostationary Earth orbit. Now, there are games to play, and I just have a couple of examples here. You can add some eccentricity to the orbit. If you look at this orbit labeled QGO relative to this inner circle that's on the equatorial plane of the Earth, QGO has the same geosynchronous period, but it has elevation and it has some inclination, and you can change where the ascending node happens in the orbit. And that, of course, leads to a sky track that is either horizontally oscillating or vertically oscillating, or even elliptically oscillating or circularly oscillating about a reference point in the sky. So that's where it gets the name quasi-geostationary Earth orbit, because from a ground observer's point of view, it's roughly in the same point of the sky. It just may wander around slightly. Now, okay, let's change some gears here and talk about IoT and some of these low power sensors. So bringing it back down to Earth, I'm going to show you a picture here that comes from an industry that I work in quite a bit, the RFID field, that shows you roughly where we've been in terms of power consumption for integrated circuits. So on the right here, or on the bottom axis here, from 1995 to 2020, here's sort of the progression of how sensitive tags are. In other words, how much power needs to come in from their antennas to power them up. You can see that the last point here, about 27 meters, corresponds to a level that's less than here on the vertical axis, about 10 microwatts. So, you know, and even though this is the last point on the graph, it really hasn't changed much. There hasn't been a significant increase in the state of the art since that time. So until about today in 2022, you get about the same sensitivity from a UHF RFID tag. And that's because the electronics are just limited in what will turn on and actually convert RF power that's received from an antenna. If it gets too weak, not only is there not enough power to drive applications like logic and memory and communications, you can't even really turn on the device. And it's that turn on voltage, not the power of the system, that actually limits today's IoT devices. So for that reason, we take 10 microwatts or negative 20 dBm to be sort of the magic threshold. If you can deliver negative 20 dBm plus a safety margin, then you can guarantee reliable space ambient operation of a sensor mode or a device. Now, I'm going to give you a reference study based on our town of Atlanta. And in this ellipse, it's an ellipse because, of course, a geostationary Earth orbit satellite would only produce a foreshortened shadow of power across the Atlanta metropolitan area. This little ellipse here is about 5 kilometers long, wide, and then about 7 kilometers tall, based on where a satellite system would be in the sky. to provide ambient power for this region of Atlanta, which is heavily populated. This is sort of the densest part of the region of the city. And we are going to do a reference study where we're going to target two systems and kind of compare and contrast them. What if you want a space solar power system that ties into the grid, provides about at least 250 watts per meter squared across an area of spot size on the ground? We'll compare that to a space ambient power system that gets at least negative 10 dBm for reception from a single patch antenna. And of course, we know that's 10 dB more than you need to basically turn on devices. And once you have a power channel, you also have a communications channel. You can backscatter to a local reader, for example, some information, some sensor information, or some sort of identification information. Now, both of these are going to be at 5.8 gigahertz. So let's compare the reference study. So here for the space solar power, this is the high powered system. I have a big disk because that disk needs to minimize the spot size for collection because I need infrastructure there on Earth. The diffraction limit says this has to be as small as possible if I want to save time, space and money on the Earth. And that's going to dictate a lot of infrastructure up here on the space solar power side of the network. And I also need a lot of area just to gather all the sunlight to focus it down. Now over here on the left are space solar power transmission parameters for geostationary Earth orbit, elevation angle of almost 50 degrees in Atlanta. And we wind up getting a transmitter and a receiver diameter that's about 1.4 kilometers. That will guarantee that the power transmitted is received here over half of that transmission. In other words, there won't be that much spillover, even if you integrate all of the side lobes outside of that little area there under ideal transmission. Now, the space ambient power network that was in the previous slide, that elliptical area that's 5.7 kilometers across, and then we said 7 or 8 kilometers on the longer dimension. I don't need as big of a transmit aperture. I can get away with 333 meters of diameter there. So that's about 5% of the surface area. If surface area is a proxy for weight and mass that you have to launch up in a rocket and put into space, that's 5% of the cost of a full space solar power system. So that's why this is a really nice proving ground, because space solar power is sort of all or nothing. You need to put the whole aperture up if you want to realize the designed spot size on the Earth. Then this is a substantially cheaper way to test out some new ideas and to develop the technology. And it provides about 21 megawatts of power when you integrate across that entire gray area, which is negative 10 dBm, about 100 microwatts of power uniformly distributed across anything with a little patch antenna facing up. In fact, that's a really nice level because you could technically get through 1 or 2 floors of residence even. You can tolerate some shadowing and some fading in that scenario with that kind of link margin. Now, I want to compare this. So, we've established it's much cheaper than what we think of as a classical space solar power satellite to deploy. And we'll get into some economic numbers at the very end. But one of the things I wanted to do in this paper, my co-author Stuart Thomas and I did an analysis to compare, well, one of the things competing with this idea is what if we had a deliberate transmitter network on Earth, like a cellular network that was providing a deliberate power. Everybody's transmitting a tone, and we try to design for that minimum neg 10 dBm point at the edge of the cellular network, at the edge of each cell, where we have basically 3 transmitters of equidistance R arriving at the receive antenna. How much more power in terms of power into our transmit antennas do we need compared to the space ambient power network? Well, that's going to be a function of the number of cells here on the horizontal axis and the path loss exponent, which in these urban areas is going to be at least 2.7, probably closer to 3.3 or even higher for the really high urban areas in that dense core. So let's just take a look at this red dotted line for now. If we have 1,000 cells, in other words, if we took that gray ellipse around the city of Atlanta, broke it up into 1,000 hexagonal cells that tessellated the area, and how much power in total would we need? And I want to keep in mind that I tried to use some realistic numbers here. First of all, you would build this network probably closer to 1 gigahertz, not 5.8, which will save you some path loss. And also, you would use transmitter antennas that would have at least 10 dBi of gain along the horizon, because you want to focus your power along the horizon. So those were some of the assumptions built into this paper that discusses the reference design. So if that's the case, then we're looking here at 1,000 cells of at least 12 or 13 dB more transmit power than the space ambient power system. Not only is that a lot of extra power, but keep in mind, if I'm driving residential or earthbound infrastructure, that power has to come from a power plant, right? Or some sort of earthbound source, which in the year 2022 is still probably some sort of problematic energy source. Maybe it's creating a lot of extra carbon we didn't need, because most of this power goes to waste, right? It's being broadcast across the environment. The sensors only use a very small fraction of it, and therefore we want to minimize the losses there. In space, you're getting a non-emitting source of power, almost, not for free. We'll get into the cost in a second, but it's in excess of what you have on the ground. You're not using an earthbound power supply to provide the ambient power. And that's important. And this is probably a very conservative analysis, because unlike space solar power and a little patch antenna that points up in the air or at the source, terrestrial links, as anybody who does wireless knows, are subject to much more stringent small scale fading and blockages. And so even at this planned designed target of negative 10 dBm of received power, you would still struggle to realize that reliably across the area. It's not uncommon to have 10 to 15 dB of extra fade margin for terrestrial links just to accommodate that. So clearly, this is not practical to do this on a terrestrial designed network that's intentionally transmitting power to get reliable coverage. It just goes to show you the difference between a bunch of inefficient point sources as opposed to the uniformity of a far field beam. Even if we have to do something acrobatic, like put a bunch of infrastructure into space, it can still be worth it. Now let's take a look at the first pass economics. Let's assume that we can make these satellites very thin. And if you think about it, this is a very two-dimensional problem. The solar collection is all about area. We can make those electronics very thin, almost arbitrarily thin. There's a reason why we don't do that practically in space or in general, because we're not necessarily worried about area density like we are in these applications. But this can be made very light. Likewise, there are ways to make the microwave transmission down to Earth equally lightweight. That too is very much a two-dimensional problem. We can make electronics not unlike our very thin cell phones that are capable of generating and synchronizing RF across an aperture that are very lightweight. The current cost for geostationary Earth orbit launch is about $30,000 per kilogram to geo. For a system the size of what we predicted 333 meters in diameter. That area would cost $7 billion to launch. If you amortize those costs without inflation across 20 years, that would be about $348 million annually to provide ambient power to the city of Atlanta. And of course, there's always an argument about how do you recoup the cost for these things? Do you incorporate a licensing fee for all of the sensors that are using like a subscription to power that's ambient? Does that open you up to privacy? Is a public-private partnership where we just sort of agree to fund it with tax dollars? There's all sorts of models out there. I'm an engineer, so I'm interested in those things because all engineers have to be interested in the business aspect of those, but there are probably better people to unwrap that. Still, one thing that the engineer in me knows that I would have to think up of $348 million of annual value-adding sensors and communications and computation features that I could add to my city to justify the cost of something like this. Now, let me go ahead and skip to the bin. Let's make one more alteration. One of the interesting things about this type of satellite system is that once you get to the 1 kilogram per meter squared, this is much less area density than a typical satellite is designed for. And what that means is that there's going to be some space effects that at first might seem detrimental, but are actually a really big blessing in disguise and create a really unique window of opportunity. In space, there is this 4.53 micropascals of solar pressure. This is not the solar wind. Solar wind are basically protons and alpha particles that are flying out of the sun, and that exists too, and that can exert pressure on a satellite. But the actual pressure I'm talking about is the pressure from absorbing or reflecting photons. Einstein says that photons, especially coming from the sun, exhibit momentum. They have no rest mass, but they do impart momentum to an object if they're absorbed or reflected. And of course, there's so many photons coming off the sun that there's this steady pressure at about 1 astronomical unit to the distance of the Earth, which will start to distort orbits once your area density drops to around the region that we're talking about, 1 kilogram per meter squared. And of course, there's ways to design around that, but there's also an opportunity here. One of the neat things you can do is once your spacecraft drops to a certain area density, you no longer need station keeping fuel. In fact, you may not even need a stage that tows you out to geostationary Earth orbit. You may be able to deploy at low Earth orbit where the launch costs are much lower, $5,000 per kilogram and dropping. This means that I could deploy to geostationary Earth orbit all of my components. They would unfurl, and then they would begin a several month long spiraling journey to geostationary Earth orbit using only solar pressure, basically where the spacecraft itself becomes the solar sail. I can do this for $435 million instead of $7 billion, which means that amortizes to $22 million annually over 20 years. That is a much more realistic number, and one can easily envision millions of sensors across a city area and functionalities that you could build into an ambient power network that would add that kind of value to the lifestyle of the residents and the businesses that operate there. So with that, I think I have 2 minutes over my promised 45 minute duration. So I'm going to just wrap this up. We've seen as it's not only possible, but also efficient to power ambient sensors and communication from space. It requires the design of space ambient power satellite systems that are low area density. Solar pressure is a factor and ultimately a good. And space ambient power can be a valuable stepping stone for other space-based solar power provision. There are a lot of other applications that benefit from this. I told you the big aim in all of power engineering is to provide pollution-free energy to the grid. However, there's also work involving space-to-space power beaming, powering vehicles from space like drones and lunar probes and things like that. Lunar power provision in general, you hear a lot in the news about wanting to put a base or a mining operation, a robotic base, or even a human base on the moon. Well, the moon experiences 14 days of solid night where the temperatures start to approach absolute zero. If you want a human or even operating electronics, you need to find ways to beam power to that location to get through the lunar night. The only way we know how to do it now is to launch a tremendous amount of nuclear material in the form of a radioisotope thermoelectric generator to the surface of the moon, which is politically untenable to do it repeatedly and lots of times from your launch sites. So, and then also things like powering a base on Mars, sensors in space. There's a lot. This is a growing field that's not just about putting green power into the grid. So with that, I'm going to wrap up, and I would love to entertain any questions from the audience.
Okay, thank you very much, Professor Durgin. Now it's time for Q&A. So if you have any question, you can raise your hand or you can ask it in the Q&A, and I will echo these questions. Okay, let me start by asking myself one question. For slide 12, the analysis that you carry to compare the cellular system with space ambient power, is it considered? I mean, are you considering the contribution of every cells in the region, or just like the adjacent cells to the point?
Yeah, that's a great question. So the paper that did the analysis works on the three closest cells. You do get a little bit more from the surrounding transmitters because unlike the cellular system, in a system like this, you can always reuse your frequencies, right? You get a frequency reuse of one, and you want to have, unlike a cellular network, you want the interference from the adjacent cells in a power network. But once you start approaching the realistic types of path loss exponents, in these environments, they turn into a fairly negligible transmission, especially in an urban area. So we neglected them in the first order analysis.
Thank you. The audience, any questions? Okay, I see. Dr. Ali, please go ahead. Dr. Ali, please go ahead. Dr. Ali Nasser. You're muted, so if you can unmute yourself so we can hear. Yes, please. Okay, I think there's an issue with these. Okay, okay, I think there's an issue with the sound. So, Dr. Ali, if you can unmute yourself. Okay, let me ask you to. Okay, are there any other question while we're trying to fix the mic of Dr. Ali? Okay, while we're trying to fix this issue, how would the issue of like low LEO satellites be resolved when you want to have constant ambient, constant solar ambient power?
So you said, how would, if you have low Earth orbit satellites, are you worried about blockage from those satellites?
Yes.
Yeah, that's a good question. So if you work through the electromagnetics of it, the satellites, any satellite that passes in front of the beam shadows the beam. Now, this is not like a space solar power satellite where you have a tremendous amount of energy. The energy density is still very low. And it turns out that you're only, if you look at a low Earth orbit satellite, it's at least a few hundred kilometers above the surface of the Earth. And at microwave frequencies, the wave diffracts around it so that there's no real noticeable shadow that gets cast upon the ground. You scatter a little bit of the energy off from low Earth orbit, but it's not even a measurable amount. And that's just because the distance from the satellite to the ground compared to the wavelength is so large.
Okay, thank you. Dr. Ali, is your problem fixed now? Can you ask your question, Dr. Ali Nasser? Okay, I have. Okay.
Oh, he typed it in. I see it.
So Dr. Ali Nasser asks this, the received power from cellular power transmission is usually very low unless we are in very close vicinity, say 10 meters. Now, if we are saying that we'll be going to use 3 base stations in the vicinity to boost the received power level, it means that we must be around 100 meters away from each base station.
That's exactly right. He grasps the numbers very well. And in fact, it kind of illuminates an issue that I glossed over in the presentation, is that it's not just about the total amount of power that you're pumping into the network here. But if you look at this, let's say we went to 1,000, so I have the slide up here. Let's say we went to 1,000 cells. And the cells are, we said, would be transmitting over 10 dB more than the tens of megawatts of power. So if we say, well, wait a second, if I'm transmitting hundreds of megawatts of power spread out over 1,000 cells, that means each cell is technically transmitting hundreds of kilowatts of power, right? And that's not realistic either. There are requirements on Earth that if you want to meet them, you can't transmit hundreds of watts. You'll be lucky to transmit tens of watts, hundreds of kilowatts versus tens of watts. So that's not even a safe level of transmission, which is the other side of the evaluation. You really do need tens of thousands of cells, probably hundreds of thousands of cells to blanket across the area to guarantee power, which is exactly what Professor Nasir picks up on.
Okay, thank you. Are there any questions from the audience? Okay, I think going once, twice. Okay. Thank you very much, Professor Durgin, and thank you all for being here. Our next presentation will be there in a few minutes. So thank you.
Well, thank you very much. Thanks for having me.
Thank you very much, Dr. Mohammed Al-Hassoun, for chairing this talk. Next, I would like to invite Dr. Wissam Misbah to take over the chairing part. And we have our next speaker, who is Dr. Ahmed Alkhateeb. So Dr. Wissam, the floor is yours. Thank you.
Thank you, Dr. Zahid. I would like to welcome Dr. Ahmed Alkhateeb, and I'm going to just mention quickly his biography. Dr. Ahmed Alkhateeb received his BS and MS degrees in electrical engineering from Cairo University, Egypt, and his PhD degree from the University of Texas, Austin, USA in 2016. And before joining Arizona State University, he also worked with Facebook as a wireless communication researcher at the Connectivity Lab. And in 2018, he joined Arizona State University, where he is currently an assistant professor. His research interests are in the broad areas of wireless communications, signal processing, machine learning, and applied math. He is also the recipient of the MCD Fellowship from the University of Texas, Austin, the IEEE Signal Processing Society Young Author Best Paper Award for his work on hybrid precoding and channel estimation in millimeter wave communication systems. And also he's the recipient of the NSF Career Award to support his research on machine learning for large-scale MIMO system. Without any further delay, I would like to welcome Dr. Ahmed Alkhateeb. Please go ahead, Dr. Ahmed.
Thank you very much, Dr. Sam, for the invitation and introduction, and thanks everyone for attending. So yeah, let me share screen. All right, you see the screen, slides?
Yes, we can see.
Yes, yeah.
Okay, perfect. All right, so today, yeah, I would like to basically present some of our research that we have been doing over the last 2-3 years on the potential value of integrating sensing and machine learning into wireless communication systems for 6G and beyond. So this is joint work with many of my PhD, master, and undergrad students, Goranj, Ahmed, Shuaw, Shwaifin, Tawfiq, Muhammad, you, Nikhil, and Andrew. And this work was and still supported by NSF and industry. Right, so let's start with the motivation. If we look now at the communication systems, so there are key trends. Two of them are the use of large antenna arrays. So currently we are moving to higher and higher number of antennas and larger arrays. So both at low frequency massive MIMO or millimeter wave and terahertz MIMO or cell-free massive MIMO or intelligent surfaces. There are basically different ways now that we are deploying larger and larger antenna arrays, but at low frequency and also at higher frequency bands. The other key trend is the migration to higher frequency bands. So going from sub-6 gigahertz before 5G to millimeter wave in 5G and probably sub-terahertz in 6G and beyond. So these key trends are mainly, if we look at these two key trends, they are mainly driven and motivated by the demand for higher data rates. So want to achieve higher data rates, so we deploy larger antenna arrays to harvest the spatial multiplexing and beamforming gains, and also go to higher frequency to access the larger bandwidth. So they're mainly driven by the interest in accessing accessing higher bandwidths and achieving higher data rates. But they lead to specific challenges that come with them. So first, if we look at the use of large antenna arrays, this means that we have larger antennas at base station, probably also at the users, and this means that we need to estimate such channel at larger number of antenna elements, or that we use narrow beams and we want to find the best beam pair where to point the beam. And this means higher beam training overhead and channel estimation training and feedback overhead. So as a result, this means that it is difficult to support, it's more difficult to support mobility with this large antenna arrays. So as we, again, demand higher and higher data rates, we want to deploy larger and larger antenna arrays, but then this becomes, it becomes harder to support mobility. Also, it imposes challenges on the power consumption, especially at the UE side, that it needs to continuously search for the beam and perform a lot of channel estimation and feedback processing. With the other key trends, the higher frequency bands, it also comes with other challenges. So for example, if we communicate in millimeter wave or above, so the signal propagation is very sensitive to, experience a lot of penetration loss and diffuse scattering, and this makes the communication link depends mainly on the communication lengths depend mainly on the line of sight, and any blockage that would block the link could also could disconnect the connection. And this means more challenges to the reliability of the network, because again, if the user, let's say, turns around the corner, then the link could be easily disconnected. If any, let's say, a base station at the street communicating with a car, and if a bus came and blocked the links, it could quickly disrupt the communication session. So so going to higher frequency makes it harder to maintain the reliability of the link. Also, with this reliability and disconnection comes a challenge for latency. So there are many challenges then for mobility, power consumption, reliability, and latency that comes with these two key trends that are motivated by the higher data rate. And if we look broadly at these two sets of challenges, we can say that the acquiring channel knowledge could be a key to overcome these challenges. Because if we assume for now that we have this channel knowledge for free at the base station and also at the user, then they can know where to point the beam, they can know how to establish how to construct the channel, and how to establish the communication or how to send the data rate and precode these MIMO streams. So if we have channel knowledge for free, let's say, at the base station and UE, then we can support mobility and also low power consumption. At the other side, if we know the channel also at the future, not just at the current times instant, but also at the future time instance, then the infrastructure and user could probably leverage this knowledge to proactively predict that a blockage is going to happen, or that the link that channel will experience some degradation and or lead some degradation performance, and can do some proactive action. For example, the network can decide to switch the beam to another line of sight or a second line of sight beam, or to switch the user to another base station. So it can do some proactive action to enhance reliability and address the latency challenges of the network. So how can we then acquire this channel knowledge? And here it becomes interesting to think about machine learning and what role can machine learning help with to address this channel acquisition idea. So let's start with the intuition. So why machine learning could be interesting? So if we look at the channels, let's say, between a base station and users, then it is generally this channel is generally defined by the various elements of the environment, including the locations of the transmitter receivers, the geometry of the buildings around the transmitter receivers, the electromagnetic materials, and so on. So intuitively, we can write the channel, and when I mention the channel, I mean the channel vector, matrix, channel covariance, beamforming. So basically, all the different, let's say, versions of the channel. So we can write the channel as function of these different elements. So the locations, the geometries, the materials, and so on. But then this function is hard to characterize analytically and changes from location to location. And here comes one interesting rule of machine learning. So that can learn how to approximate and learn this difficult to characterize mapping function from all these inputs, the environment, geometry, materials, locations, etc., to the channel vectors and beamforming vectors. And the key trick here would be if we can extract, if we have a way to extract features that model these inputs with low training overhead. So if we can do that, and then if we have this machine learning models that knows how to map these features to the beamforming and large dimension channel vectors and beamforming vectors, then this means that we can maps these features that again can be acquired with low training overhead to channels and beams of large antenna arrays that require large training overhead. And here we can somehow overcome these challenges that I mentioned. So the next question then is, what are these features? So how can we extract these features that that model these inputs? So I'll talk about this in a minute. But before we go there, like it's interesting to notice that as we go higher in large antenna arrays or larger in antenna arrays and higher in frequency bands, so we get these challenges that I mentioned, but also interestingly, these two key trends lead to a higher dependency on the geometry and the different geometrical aspect of the environment, including the user locations and geometry of the shape and orientation and mobility pattern of the users and different scatters in the environment. So this means what? This means that if we have knowledge about this user position, the geometry, the other objects, shapes and positions and orientation, mobility patterns of the different objects in the environment. So this could further help the communication systems in making decisions on what is the best beam-forming vector, what's the, for example, I mean, as we go to higher in frequencies on the length, again, as we discussed, kind of gets very sensitive to blockages. So if we know that there is a bus moving and we have this geometrical information about what's happening in the environment, then we can proactively, again, predict that this bus is going to block the link, and then we can hand off this communication station to probably another base station or switch to another beam. So as we go to higher and larger antenna arrays and higher frequency bands, the communication system becomes more and more dependent on these important aspects of the communication environment. And this is interesting because this means that if we have some knowledge then about the position, geometry, mobility patterns, etc., then we can potentially leverage this knowledge in enhancing and helping the communication system. And this is exactly the motivation behind sensing-aided wireless communication, where in general, we imagine a system where both the base station or the infrastructure nodes and mobile users, they have deployed different kinds of sensors, all the way from radar sensors to GPS positioning to camera, LiDAR, radar, IMU, other types of sensors, and leverage all this sensing information or sensory data to provide or to acquire some awareness and information about what's happening in the environment, including the position and mobility pattern and orientation of the user and the other moving scatters and stationary scatters in the environment. And then once the network has all this information, it can help in making decisions on the beam, on the channel covariance, on the blockage prediction, on the user scheduling, handoff, and so on, without necessarily requiring to acquire this large dimensional channel information using the classical over-the-air training approaches. So in a way, so this is, I mean, think of this as a way to acquire the channel knowledge almost for free in terms of the wireless communication resources, while still being able to address all these important decisions. And this goes back to the point I mentioned in the previous few slides, that if we can acquire the channel for free, then we can potentially know how to support mobility and reduce the power consumption and increase the battery life of the users' devices, address the reliability and latency challenges in wireless networks. So the next question is, then what are these sensors and how can we make some progress in, let's say, testing the visibility of these ideas in reality? So in general, we can look at sensory data as two big classes. I just classify them into two classes. One is wireless communication receivers as sensors. It's important to note also that the receivers, the wireless communication receivers, they're one type of sensor. So we can look at the information, the spectrum information and the channel information that we acquire from the antennas. as also some type of sensory data that we can potentially leverage also in reducing this channel acquisition overhead. And then it becomes, interesting to ask why would I need to deploy wireless communication antennas to help in channel estimation, or use channel estimation to why would I estimate that channel at some antennas to help in reducing the channel estimation overhead? So I will clarify this in the next few slides. And the other type of sensors is, can think of them as just all the other type of sensors that are not receivers, not communication receivers, for the sake of no better name, but it's interesting to look at all these other classes of sensors, such as position, GPS positioning, or other type of positioning, camera, radar, LiDAR, and so on. So all these types of sensors, they also provide a lot of information about what's happening in the environment, and then it could be potentially be also leveraged to reduce this channel acquisition overhead. So in the next, in the remaining slides, I will just discuss, just dedicate 2, 3, 4 slides for the first type of sensors, this wireless communication receivers as sensors, and then we'll spend the rest of the talk on the other type of sensors. So to get some sense of why wireless receivers as sensors could be interesting in addressing this channel acquisition problem, we formulated this concept of channel mapping a few years ago, where essentially the idea is that if we have two sets of antennas, so let's say we have one communication environment where we have 2 sets of antennas, M1 and M2, and these 2 sets of antennas are communicating with the same mobile user, and that can take a certain set of locations. And these 2 sets of antennas could generally be at 2 frequency bands and at 2 different locations in the same environment. So given this setup, so we'll define 2 mapping functions, GM1F1 and GM2F2, that maps the locations as the location of the user to the channel at the first and second sets of antennas. So these mapping functions exist just by construction from the channel, from the propagation. So here, assuming that for simplicity, can think of it as basically this user can take a certain quantized set of locations, and then for every location, we have a channel info vector or matrix at the first set of antenna and the second set of antenna. Now, we'll make one assumption, and this is the only assumption that we need to basically make here. So that the only assumption is that we'll assume that the mapping from the position to the first set of antennas, which is channels at the first set of antenna, just the first set of antenna, is bijective, which means that every location will lead to a unique, so any location leads to a unique channels at the first set of antennas, or 2 different positions will lead to 2 different channels at the first set of antenna. Now, how practical this assumption or condition is, so we can also discuss this in a minute. Now, if this condition is satisfied, then this means that the inverse mapping exists, which means that if we know that channel at the first set of antennas, then there exists a way to map this back to the position information. And this means that there is a composite mapping also that can map the channels from the first set of antenna directly to the channels at the second set of antenna. Okay, so basically, if this mapping is bijective, then we can map the channels at the first set of antenna to the position, and then from the second mapping, we can map the position to the channels at the second set of antennas, and then if this 2 mapping exists, then we also can map the channels from the first set of antenna to the channels at the second set of antenna, or this mapping exists. Even if we don't know how to do this mapping exactly, given the environment, geometry, and characteristics, but if the first mapping exists, is bijective, then this composite mapping exists. And once it exists, then using the universal approximation theory in neural networks, then it exists large enough or complex enough neural networks that can learn how to do this mapping from the channels at the first set of antenna to the channels at the second set of antenna. Now, before we discuss why this could be interesting in addressing this channel acquisition problem, just want to highlight quickly that this bijectiveness condition is also part of fingerprinting inverse fingerprinting problem. So if we, or basically all these positioning ideas using channel information. So if we know that the channel, basically, then we can go back and identify the position. And in practice, this could be satisfied with reasonable number of antennas. So if we have, again, set of position information and we have channel, if we look at the channel at 8 or 10 antenna elements that are distributed in the environment, then this channel mapping this mapping from the position to the channels as the first set of antenna will likely be bijective with high probability. And there are some papers that discuss how practical this assumption is. So if we believe that this bijectiveness condition could be satisfied, at least for deterministic cases, then this means that if we know the channel at the first set of antenna, again, then we can map this information to that channel at the second set of antenna. Now, why this is interesting? The interesting point here is that we didn't make, in order to derive this this conclusion, we didn't need to make any assumption on the two current antennas are operating, two sets of antennas are operating in the same frequency band. So they could operate at two different frequency bands. Also, we didn't make any assumption on the number of antennas at the second set of antennas. So we only need to have sufficient number of antennas in the first set of antenna to ensure this bijectiveness condition. But once it is satisfied, we can map this information to any number of antennas in the second set. And this could be used in multiple applications. So for example, if we look at this channel mapping in frequency, so this means that if we, so again, as a special case of this mapping result, if you assume now that the two sets of antennas are just the same set of antenna, but at two different frequency bands, they're operating at two different frequency bands. For example, like FDD massive MIMO, where you have the uplink is happening at one frequency band and the downlink is happening at another frequency band. In these communication systems, it is very hard to acquire the downlink channel because it requires channel training of all the antennas and then the feedback of the user, while it is easy to acquire the uplink channel because it may require just one or a few pilots from the user to acquire that channel if it is fully digital simultaneously from all the antennas. And now using this channel mapping in frequency results, this means that if we acquire the uplink channel at the base station, so the base station can learn how to map this channel information directly to the downlink channel so that it completely eliminates the need to do channel training and feedback for this downlink channel, which can significantly improve the performance. Of course, to do that, we need to do two things. First, we need to guarantee that the uplink channel mapping is bijective, meaning that we have sufficient number of antennas for this given environment such that any two positions of the users lead to two different uplink channels at the second set of antenna, which is, again, in practice with massive MIMO is not hard to guarantee. The second, of course, is that this requires some sort of training phase. So assume that the communication system, when it starts, it will run maybe as normal for some time to acquire uplink and downlink channels. And then after acquiring enough data set, it could train this machine learning model to learn how to map this, this channel information. But then once it is done, then this can significantly reduce the training and feedback overhead, again, enabling mobility, reliability, and low latency in massive MIMO systems. There are different ways also you can think of this channel mapping or application. So you can think of this also as a way to acquire millimeter wave channel and beam information using sub-6 GHz channel information, which is, again, very interesting because if the sub-6 GHz channel, first, most communication systems now are dual band, and 5G and beyond will likely be also dual band or multi-band. So they would be operating at lower frequency as well as millimeter wave. So imagine now a scenario where a base station and user, both of them are operating at sub-6 GHz and millimeter wave. So if we acquire this sub-6 GHz channel information at the base station, which is, again, relatively easy to acquire with a few pilots, then we can use this information to directly predict what is the best millimeter wave beamforming vector that this base station should use, let's say, to downlink serve this user, which is, again, at millimeter wave, it is hard to acquire this millimeter wave beam training, beam result that typically with large antenna arrays requires large training overhead to find where is the best beam. So also in space, so channel mapping in space could find interesting applications. For example, in FDD massive MIMO cell, we can also think of this one value here is that instead of training and feeding back all the channel information from the, say, 64 antenna massive MIMO system, we can potentially just select a subset of these antennas and downlink and feed back the channel from this subset of antenna, and then use this information with this channel mapping in space. So now you think of this subset of antenna as the first antenna set, and the rest of the antennas as the second set of antenna. So if we know the channel at the first set of antenna, and if this again mapping is bijective, then we can predict the channel at the second set of antenna, or this full antenna array, or full MIMO system, which again can significantly reduce the training and feedback overhead. So imagine, like, instead of training and feeding back 64 antennas, so maybe 8 antennas or so. So we have a lot of results on all these actually different mapping cases in our publication. So if you are interested, you can check like more details there. And of course, please feel free also to contact me anytime. The other another also application could be found in cell-free massive MIMO system, where we have maybe distributed a large number of antenna terminals. Now, instead of acquiring the information at all these terminals and feeding back all this to the central unit to process and predict the precoders, if it is some sort of distributed precoding, centralized precoding design. Now, with this channel mapping, you can imagine that you can maybe feed only a few subset of these channel information to the cloud or the central processing unit that processes this information to design, let's say, the precoding for the rest of the distributed antenna terminals. All right, so this is again an interesting topic with a lot of potential extensions, but I would stop here and go to the second, move to the next class of sensors, which is non-communication sensors. And again, if you have any questions on anything, please let me know. So now this second class of sensor is probably less obvious why it could be interesting for communication systems. But if we go to higher frequency bands, especially, so the communication systems, again, and again, large antenna arrays, finding, let's say, beamforming vector, finding what is the best line of sight beams that serves the user, can potentially benefit from knowing the location of the user, right? If we know if the base station, let's say, knows the location of the user and in the line of sight scenarios, then intuitively it can know where to point this beam. So the advantage of what we call position-aided beam prediction in millimeter wave and terahertz or sub-terahertz systems is that it can potentially reduce the training overhead, the beam training overhead, and it may not need a lot of processing complexity to figure out this relation between the locations and the channel or beam information. But then the challenges with position information is that it is it has some ambiguity in general. So if we in this mapping between the position and the beam, so if we know the position, this may not be sufficient to figure out the beam information in non-line of sight scenarios. So if it is line of sight, it might be obvious, but if we have non-line of sight scenarios, then depending on the location of the user and the type of blockages that are between this user and the base station or the infrastructure or the other side of the communication side, this could mean different beamforming vectors. So there is some ambiguity in just relying on location information to predict the channel on the beam. So we need more information about the environment. Also, location information, of course, there are a lot of interesting new work on how to improve positioning, and you're also doing some research in many of these directions. But in general, acquiring position information may need a lot of calibration and has a lot of overhead. And I will elaborate more on this in a few slides. So if position information is not sufficient, then what else can we add to this information to further improve this awareness about the communication environment and help in this beam channel acquisition problems. So we asked this question 2019 is basically can vision help in wireless communication? If you look at most communication devices, AR, VR, mobile devices, even autonomous vehicles, and probably also we can add, they all have cameras, and potentially also we can add cameras to the infrastructure, at least in public locations. So if we have this cameras added to the infrastructure and the mobile users, can we potentially leverage this visual information to help the communication system? And this becomes particularly interesting as we go again to millimeter wave and sub-terahertz systems, because these systems rely on line of sight links. So the base station and users, they are in line of sight, close to visual line of sight to each other. They can, so the base station can literally see the user. Also, these communication systems are very sensitive to blockages. So if the base station can see that a blockage is going to block this link to the user, to this line of sight users, then this information could be actually very interesting in addressing these reliability challenges to identify if the user is going from outdoor to indoor, and to do proactive handoff and network management decisions. So in order to make, however, any progress in researching these ideas, so we need to have a data set that with coexisting communication or wireless communication and visual data. So in order to do that, so we constructed this YY data set and again around, so we have been working on this 2018 to 2020. And in this vision wireless data set, we basically try to use synthetic high fidelity synthetic data generators such as Blender and to generate visual data, synthetic visual data, that's a game engine, and Wireless Insight, which is a 3D accurate 3D ray tracing to generate wireless propagation data. And then we try basically to build the same environment scenario and use it in Blender and Wireless Insight to generate these two types of modalities, of data modalities. And then with that, we have coexisting data sets, which means that, again, let's say a base station and user and in a certain environment, when this is visual data, then this is wireless data. So we can basically have the two types of data for the same time instance as this in this environment. So now that we have this coexisting data, so this is a sample of the data set where we have basically, this is all synthetic data, and we have, we use this the wireless propagation that is collected in the same time of this visual data to identify where to point the beam. So for example, here, this network decides to that this beam is line of sight. Here it's not line of sight, so the base station points to a reflector. Here it points also to a reflector to reach this user, and so on. So basically, we can see that the wireless information makes sense, let's say, based on the environment and the user location. So we use this data set to study very basic problems such as beam prediction using visual data. So in a very simple case where we have one vehicle moving in front of a base station, and then we use this visual data with, let's say, ResNet 18 neural network model with customized last layer to fit this beam classification task to identify where is the beam. So here's this is a real results where we are using, again, this visual data, feeding this to the neural network to predict the beam without using any wireless communication resources. So we are not putting any overhead on the network, or at least using this visual information to reduce the beam training overhead. So instead of searching over, let's say, 64 beams, so we can use this visual information to suggest, let's say, what are the top 5 or 4 or 3 beams that the base station should use to kind of refine the beam direction. We also looked at other problems such as block prediction. So if we use this visual data and with this beam information, can the network leverage this, again, visual data to realize when this link is going to be blocked in the future and make proactive action. So I go a little bit faster here. So that was great, but then the question that was always asked is, can we realize these gains in practice? So as we go to practice, there is the sensing information will have noise, acquiring the sensing information will have latency, and also in practice, there are a lot of dynamics and a lot of variables that would be interesting to explore the potential and feasibility of using these sensing data in reality to help wireless communication decisions. So in order to do that, so we started building this, what we call a deep sense dataset, which is a large scale, real world, multimodal sensing and communication dataset that comprises coexisting sensing and communication data. So it's again the same idea of YY, but using real data, where we essentially have multiple units, and every unit is collecting. So this unit could be a base station or a infrastructure node, a user or mobile vehicle, let's say node. Every node or every unit has a number of sensors and collecting sensor data. And then offline, we synchronize all this data. So make sure that at the same time, to some very, let's say within 20, 30 milliseconds, that was camera information that's collected from the base station or the infrastructure node. That was the radar image, that was the LiDAR sweep, that was the millimeter wave beam training result, and so on, or position. So all this information, we synchronize them so that we have eventually a set of data points. Every data point has coexisting sensing and communication data modalities. And we have several sensing data, so including camera, radar, LiDAR, position, and millimeter wave beam training, and we are also adding sub-6 GHz MIMO system. Now using this, okay, yeah, before I go to the applications. So far, just a summary of the dataset. So the dataset is available now online, and you can, I mean, anyone can access and use this data. We have so far more than 1 million data points, multimodal data points. So 1 million points, everyone has multiple modalities. Most of the data has beam training, camera and position information. And some of the scenarios, we have also radar, LiDAR, and IMU. So so far, we have also collected this data or this 1 million plus data points are collected over 30 scenarios that include or that try to cover different use cases such as vehicle to infrastructure, communication with pedestrian, drones, robots, application and controlled indoor environment. We tried also to make sure we have also reconfigurable intelligence service scenario at sub-6 GHz. And we try to build these also scenarios to emulate different or to kind of to address several important basically let's say corner cases, and for example with enough diversity and variance. So for example, we have visual data that are collected in the day and night, a little bit different weather conditions, not much. And with different distances, let's say between the base station and users, different traffic conditions, different orientation and field of views, and so on. So that the hope here is that now with this data set, where this is one scenario of the data, so we have also generated this. We have also generated this kind of visualization for every scenario, so that it can be easily debugged. So, for example, if a certain sample you have beam information that you don't know if it makes sense or not, so you can come back to this video to go to the right sample number and figure out, you know, visually what was how the communication environment looked like, and the beam information, position, and other modalities. Now with this data, so the hope here is that this data now enables a lot of interesting, or the study, or the way to study different communication and sensing and positioning applications. So for example, in communication, so we can now use this data set to study things like beam prediction, tracking, future beam prediction, block prediction, proactive handoff resource management, and others applications, and also in positioning and ranging, imaging, detection and classification. So we are also adding more sensing information that would enable hopefully electromagnetic imaging very soon. And then now, given this large data set that are collected in multiple locations with sufficient variance, now we can study these interesting questions on transfer learning, few shot learning, learning with limited data fusion, and so on. So all these kind of interesting machine learning questions were actually the main motivation behind building this data set, that we have a way now to study how to scale these machine learning solutions in reality, in real world deployments. So now with this data set, as I mentioned, can enable a lot of interesting machine learning development and benchmarking solutions. And that was actually one also main let's say consideration we had in mind where we were building this data set, is to build it in a way that would really enable benchmarking and comparisons, so that we kind of follow the steps of computer vision and other machine learning, more established, let's say, machine learning communities, where they have very standardized ways in building data sets and offering this data so that people can easily benchmark, open source their code, reproduce the results, and compare. So for that, we also offer this data set in what we call task-specific way. So it's task-specific development data sets. And this is really one kind of hopefully easy way to enable reproducibility and benchmarking. So every task, so for example, vision-aided beam prediction as one task, where we use camera information to help the beam prediction and selection decision. So here we share basically training, validation, and test sets, so that anyone can use, again, the same exact training and validation sets and test sets to benchmark and to evaluate their solutions. And then hopefully we have, you will be hopefully excited to compete and be added to this leaderboard table. All right, so in the remaining 10 slides, I will 10 slides or so, I will go over 2 applications that this data set can enable, and then we'll try to use very initial results to address some of the important questions. So first task is sensing aided beam prediction. So again, I mean, as I tried to highlight in the beginning, so beam prediction or beam selection and tracking, so this is one of the key challenges as we go larger in antenna arrays and higher in frequency bands. And it's really one of the main, let's say, challenges that make the high adoption of these frequency bands in access scenarios harder. So if we have a way to figure out the beam direction and track the beam with the user as the user moves, without consuming wireless communication resources or with consuming much less wireless communication resources, then this has the potential of enabling these interesting enabling these to communicate over these frequency bands with larger antenna arrays, and then realize this high data rate gains. So now with this data set, we have position, LiDAR, radar, and vision information, and we can use all this information and beam information, by the way, also. So we can use this beam, let's say, to predict future beams as well, using mobility patterns. So we studied this in multiple ways. So first, we started by looking at position-aided beam prediction. So again, if we look at in line of sight scenarios, so it's kind of very, let's say, intuitive application, where if we know the position of the user in a line of sight scenario, then intuitively we should be able to predict the beam. But then how does this really work in reality with real noise in the position information and in the wireless information? So to do that, so we picked 9 scenarios out of DeepSense, and then in this 9 scenario, we have the position and we have the beam training power measurements. And then we looked at different code box sizes at the base station. We can use 64 beams or 32, 16, and so on. And we designed 3 machine learning models based on lookup table, nearest neighbor, and neural network, to also look at, do we really need, let's say, more sophisticated machine learning models, or just lookup table is enough? And then the question is, will this performance be close to synthetic data results? So again, intuitively using synthetic data, if we know the position, then we should know the beam was maybe be a 90-something%. But then in reality, what we found is that in most of the scenarios, this beam prediction accuracy, the accuracy in predicting the right beam from the first time is mostly below 50%. So 50% of the time we actually don't, this machine learning model cannot predict the best beam, the best ground truth beam accurately. So which was interesting, right? I mean, if again, intuitively, if you have this line of sight, if we know the position, we should be able to know the beam. Now, if we look at lower codebook sizes, so we get better performance. Because again, if we go to 64, so we have 16 antennas, so there is some overlapping between the beams. But even with 16, we don't reach this 90-something%, 99, 98%, where we typically see in synthetic data. So this is, I think, one important observation is that, again, I mean, as we study these machine learning problems, how well the synthetic data actually has, and the conclusions that we get from synthetic data are. So can we just rely on these conclusions that we get from synthetic data to trust that these solutions and these machine learning, let's say, models will work also in reality, or do we really need to train them also on real data, and that the conclusions could be quite different. Now, if we look at the power loss, and now another question is this beam training or this beam selection accuracy is actually the right metric to use? So is it right to just look at beam prediction accuracy and say, like, what is the accuracy in predicting this ground truth beam, or no? So here, to do that, we looked at also other metrics. So one particular one is power loss. So we see, like, what is the loss in average loss in the power of the predicted beam compared to the ground truth beam. And this is particularly useful or important because it is closely related to the end objective of this beam prediction task, which is the communication. So we want to increase, let's say, data rate of this communication link, which is tightly coupled or tightly related to the power. So if we know that we are within small power loss, then regardless of the accuracy number, I mean, it's still good. And this is now promising because if we look at the power loss, it stays within 3 dB in most of the scenarios. So this is, again, another point that beam prediction accuracy may not be the best metric, and we may be a little bit misleading, and also not very tightly coupled to the end objective. And probably looking at other performance metrics such as power loss and adopting this actually integrating this in the machine learning model design as well could be useful. So now another way to look at another also approach for this beam prediction or sensing aided beam prediction is to leverage radar data. So now if we have this radar information, let's say the base station has a radar that collects some radar images of the environment, and then use this information to help this beam prediction to predict the best beam for this user. So to study this, we also we designed. Now the interesting thing in radar is that we know how to do a lot of signal processing with the radar compared to, let's say, some of the other modalities. So now we can leverage this information or this knowledge to domain knowledge to pre-process this data before we just input them directly to the neural networks. And this can potentially reduce the complexity and inference time of the prediction. So to do that, we use basic radar processing and extracting range, angle range, Doppler, or velocity maps, and then we use this information to feed as input to the neural networks. So we have FMCW radar with 5 GHz bandwidth, 3 transmit antenna, 4 receive antenna. So it's relatively low resolution radar. And now the interesting question is that can we use this low resolution radar information to help in addressing this beam prediction problem? So in these initial results, again, what we found is that, and we compared again with this neural network approach with classical or more, let's say, classical solutions based on lookup table and object detection, which are still machine learning solutions, but with lower complexity. So overall, we found that with radar information, some kind of more with different machine learning solutions, we can achieve up to 90% what we call top K beam prediction accuracy. Top K is basically, it means that the best beam is within the top 5 predicted beams. So if we look at machine learning models, the output, and we pick the top five most promising beams predicted by the network, then the ground truth best beam is one out of these 5. So we can achieve up to 90% accuracy in beam prediction. So this means what? This means that instead of the need to do training of over 64 beam codebook and requiring 64 training overhead worth of complexity, so now we need only 5 beam refinement steps. So it's basically 1 order of magnitude less training overhead. Now, if we have also antennas at both sides of the length, this reduction could potentially be much more. I think can easily reach 2 orders of magnitude. We also looked at latency and network complexity, but one particular basically questions that I kind of wanted to or point that I wanted to highlight here is that latency is always you'll always think of latency as one challenge for this sensing-aided communication. And this could be generally true for if we want to predict instantaneous beam or make an instantaneous decision, like real-time decision. But if you, so the reason is that most of these sensors like radar or LiDAR or visual data, they need tens of milliseconds to actually acquire the data and process and make inference. In fact, inference is machine learning inference is the least time required in this process, but the acquisition of the data is the most challenging task in terms of the acquisition latency. However, if we want to, we can also think that we can use the sensing data to predict something in the future. So, for example, in a near real-time fashion, so we can use maybe a sequence of sensing information, radar information that are collected maybe over 200 milliseconds to predict the beam in the next maybe 10 instances. So now if we look at predicting in the future, we can still leverage the sensing data to reduce the overhead while not being very sensitive to the latency of this acquisition overhead. We also, now another question is in sensing is, how can this work in multi-object scenarios? So if you have just one vehicle moving in front of the base station or the camera, then it's intuitively simple, right? With simple computer vision based object detections, you can detect this vehicle and just to learn how to map this or angle information to the beam. So it was interesting to look at now how can we extend this to multi-candidate and multi-user scenarios. So to do that, we need to have another attribute for the users that cannot differentiate between these 2 vehicles just visually, which one is the transmitter. So we need to know another attribute about this transmitter. This could be location, this could be beam information. So we can probably use the beam information for a few samples to predict the beams in the future and to identify the vehicle. And then once we do that, then we can just use visual data to continue tracking this vehicle in as it moves through maybe the street. So so to do that, so we developed this several actually multimodal, what we call multimodal, what we call transmitter identification solutions, where we use multiple sensor data to identify which object in the scene is the transmitter, and then use this information to basically be able to extend the sensing aided wireless communication applications to multi-candidate and realistic now scenarios. So this is a live demo that we did where we use position and visual data to identify the vehicle and compare this to in the existence of other what we call distractors in the environment, and we see that the solution was able to correctly track the user. We can also extend this to other scenarios like drone communication, which is also one of the scenarios in the deep sense dataset. Okay, so there is also another application, block prediction. So essentially using the sensing to predict if the link is going to be blocked in the future or not. But I guess for the sake of time, I will skip this. And if you are interested, can discuss, of course, more. So in conclusion, going to higher frequency bands and using larger antenna arrays are key trends in current and future communication systems, and this will continue to scale. So the main way to address to get high data rate, and this will continue to happen, is by deploying larger antenna arrays and going to higher frequency bands. Now, as we try to scale the MIMO systems, we start getting a lot of challenges in mobility, reliability, latency, power consumption, etc., that are fundamentally attributed to the channel acquisition overhead on the wireless communication resources. So sensing and machine learning could provide an interesting way to address this challenge by relying on other out-of-band or other types of resources to obtain this environment awareness, and which are interestingly become more interesting as we go to higher frequency bands and larger antenna arrays, and use this environment awareness to help make these decisions on the beam, the blockage, the mobility, and enhancing reliability. So with deep sense and with this with these interesting applications in sensing aided wireless communication, there are many interesting future research that need to be done. In fact, what I present just scratching the surface. Extending all these applications on beam prediction, blockage prediction, future beam prediction, handoff, network management decisions, sensing, and using this wired communication and sense by fusing these different modalities and by developing better signal processing and machine learning solutions. All these are interesting open questions. How to enable the scalability of these systems in terms of machine learning model development and learning and making decisions on transfer learning, data fusion, and how to adapt to different scenarios and distribution shifts, and all these an interesting machine learning questions that need to be addressed. So with that, I will stop here. So if you're interested, so the data sets and also we open our scripts for most of this research, and we publish this on the dataset websites. So thank you, and I'm ready for questions.
Thank you very much, Dr. Ahmed, for the interesting talk. And let's open the floor now for any questions. Please raise your hand if you have any questions. Any questions to Dr. Ahmed? Okay, Dr. Ahmed, until we get any question, but let me ask maybe a basic question. In slide number 9, you talked about mapping between two different sets of antennas. You said that using maybe the knowledge of the channel from one antenna or one set of antennas, we can map it to another channel or to another set of antennas or another frequency. Why this mapping exists? This is my question here. Why is it guaranteed that this mapping exists? Can it be dependent?
Yeah. So I would first just to be more specific. So here we are assuming a deterministic scenario, and we extend this later on to dynamic scenario where we are, instead of predicting channels, we are predicting channel covariance. But if we look at this static deterministic case where we have two sets of antennas positions that can take certain set of candidate positions, and users that can take certain set of candidate positions, and static environment around them. Now, in this scenario, as we derive here, actually, so the only conditions that we need to be satisfied to be able to prove that this mapping exists, and in the paper we have more formal proof as well, is this bijectiveness condition. So once we prove that the mapping from the position to the channels at the first set of antenna is bijective, meaning that again any two positions will not lead to the same channel. And intuitively, what is the probability that two positions will lead to the same complex channel vector with the propagation and multipasses if you have, let's say, 8 elements, right? So if you have 8 elements channel vector, what is the probability that two positions will give exactly the same or very, very close to channel vector? It is intuitively very low probability. Yeah. And some papers that try kind of move try to take this in more depth But in fact, I mean, yeah, I mean, intuitively was a small set of antenna, and this condition could be satisfied with high probability. And then once it's satisfied, it means that, again, mathematically, it means that there exists a mapping from the channels at the first set of antenna to the channels at the second set of antenna. However, mathematically characterizing this mapping is very hard, and because it depends on everything in the environment. So, and this is why machine learning, you know, is interesting, that with large and complex enough neural network, if the mapping exists, then there is a way to learn it. So that's the interesting thing.
But this is the case of static, like a completely static environment. Yes. Everything is static. If you change the environment, then the model of the neural network would change, right?
Not
the parameters. Let me say that the parameters of the neural network would change.
Not necessarily. So now, if we go to dynamic scenarios, predicting now that the exact channel vector becomes hard, because it's, you know, predicting the exact complex channel vector becomes hard. And here, what I think it will be more practical to predict channel covariance instead of channel vector. So predict, let's say, if we have 64 antennas in the second set of antennas, so we have 64 dimensional space. So we can potentially leverage this channel mapping concept to predict what is the most dominant 3-4 dimensional subspace in this space. And then still this means that we are reducing the overhead of training and feedback from 64 to maybe 4 dimensional space. So it's kind of a lot of reduction on that overhead, while still now relying on classical over-the-air pilot training and estimation to refine and estimate the actual channel. So this is from the operation perspective. This is what I think is more practical, that we are developing some sort of hybrid solution where we use machine learning to predict statistics, and then use over-the-air training to predict the actual and refine to predict the actual channel. Now, in terms of machine learning, for this application, this dynamic scenario, you can learn one machine learning model that absorbs basically all these dynamics if it trained over large number of scenes, let's say, in this scenario.
Yeah, okay, thank you.
Now, if you go to a completely different city, then maybe, yes, maybe we need a new machine learning model, right? So if you go to a completely different, let's say, part of the street, then now we may need a different neural network model.
Yeah, that's what I was talking about. Yeah, if you
exactly.
change,
and here becomes,
yeah,
exactly, and here becomes interesting to like study like how can we do this model generalization or scalability, or can we use one model that fits all, and or should we do the site specific? So these are exactly the set of questions that that we hope this kind of like data set, a real world data set measurement based data sets could hopefully enable the research to answer these questions.
Thank you very much. Abdul Majid Lawal, Dr. Abdul Majid, go ahead, please. Dr. Lawal.
Dr. Wissam, we have a question in the chat. If you can read out, please.
Okay.
Then I will give access to Dr. Abdul Majid.
It's not a question, I guess, or let me see.
This is from Professor Chidad.
Okay. Some sound difficult. Some bijectivity of the mapping can be. Let me see. Let me just remove the participants. Okay, some bijectivity of the mapping can be achieved with a high probability given a large number of antennas in area 1. Would it be practically possible to use a random mapping between areas 1 and 2 with, say, antennas spatially uniformly distributed in area 1 to have maximum entropy? If so, how would this random mapping compare to the deterministic but quasi-bijective mapping used in your scheme? It's a very long question. Maybe I can repeat it to you, Dr. Ahmed, if you didn't.
I can see it. So it's this.
Oh, okay. You can see the chat. Okay.
Yeah, I mean, if I understand correctly, I mean, it goes along the same line of thinking and discussion we were discussing basically that, yes, I mean, in reality, it's, I mean, statistical we may need just statistical bijectivity, and also may only be limited to statistical channel prediction, which I think is the way to go. And we have actually a journal paper written on this, and yeah, hopefully we'll be able to submit it soon.
Okay.
But I can share with you actually if you are interested, so we can I can share it with you now.
Okay, Dr. Lawal, do you have a question? Okay, Dr. Ali.
Yes, I have a question.
Go ahead, Dr.
Okay,
Lawal.
thank you very much for the excellent presentation. My question is very trivial. So from your training, from you using the deep neural network, what is the typical channel size that you consider? Also, have you used different machine learning approach, and which one do you think is the best for channel estimation in this context?
Yeah, so it really depends so in terms of dimensions. So dimensions, vary depending on the system consideration. So in our simulations, if you mean our simulation, it depends again on the exact study. So for example, we try to adopt like realistic numbers, I would say, for the number of antennas. So for example, in this massive MIMO FTD channel prediction, so we're assuming 64 128 antennas, lower frequency, maybe 256 512 millimeter wave. Yes, we normally try to pick realistic numbers for the number of antennas to study this, and channel size of the channels, of course, is defined accordingly. For the machine learning model, it also really depends. So on the specific machine learning task. So yeah, we looked at several things. So all the way from we normally start with simple machine learning model to see like if it works or not, and then we go to before we make things complicated. And in some machine learning models, we designed them actually. So in some neural networks, we designed them to account for hardware constraints. For example, if we have analog only beamforming or hybrid analog digital beamforming and hybrid analog digital transceiver architecture. So in that case, we cannot assume that we have the channel from all antennas simultaneously at the baseband. And in these cases, we need to design the neural networks to account for these hardware constraints. So in some cases, we designed hardware-specific neural networks that were, let's say, the neural network weights, they account for, let's say, the phase shifter constraints on this analog transceiver. Yeah,
Okay, Dr. Ahmed, I apologize for that, but we are running out of time and we need to move on. I apologize also for whoever raised his hand for any questions, but you can contact Dr. Ahmed by email later or offline or during the conclusion of the forum today. Thank you, Dr. Ahmed. Thank you very much. I will give back the floor to Dr. Zahid. Thank you.
Thank you very much, Dr. Wissam, and thank you very much, Dr. Alkhateeb, for the talk. So now I think we are at the last part where we are going to have our panel discussion and the closing remarks. So I am now going to give the floor to Dr. Adi Al-Muqabil. Please, Dr. Adi, if you can.
Okay, Bismillah ar-Rahman ar-Rahim. Again, I'd like to thank all the speakers for very interesting speeches. I think we have very limited time and we are getting late in the day. So if you allow me, I'm planning to have like a concluding remarks. So if you want to prepare yourself, Dr. Ahmed, Dr. Durgin, like just think about what the concluding remarks would be. I will pose a question. If you're approached by a young professor or a graduate students ask you for a specific topic out of what you presented to start working on, a topic that will span few years to come, being a hot topic, and you can publish out of that. While you are thinking about the answer, if we have Dr. Moeness, Professor Amin Moeness Amin, do we have Professor Moeness? Are you around?
Yes, 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 yes.
Dr. Moeness, yeah, we enjoyed your recorded message, and I would like to give you some few minutes if you want to whatever in your mind you want to comment about the topic or.
Yes. First of all, my apology. I had a red eye. I flew back from California, and actually I haven't slept yet since I arrived at 2 a.m. But
congratulations, Dr. Moeness, for the prize.
Congratulations.
Yeah, thank you. Yeah, in fact, I was there receiving the medal, and it went very well. So I really thank you. Yeah. So certainly there are many hats a person can wear when talk about integrated sensing and communications. So I heard part of the previous talk, and certainly it's very impressive. But if you talk to other groups or other research agencies, their thinking could be completely different. So part of the things I mentioned in my talk really comes from the overarching definitions. I'm talking about RF, so I'm not including camera and communication, I'm including radar and communications. So the question here again is a coexistence issue where the sense and communications not only they need to share the platform, the same platform, electronics and all the things, right? But there is a primary, there is a secondary user issue about who would yield and who would lead, right? And now we see that many papers actually dive into the math, right? If you open the transactions on communication signal processing, you would see a constraint minimization problem, and they throw in the mutual information, they throw in some of the capacity constraints, and they solve the problem without really understanding what the practical issues are. And so it has becoming a mathematical driven research problem. Right? So I'm glad that Professor Ahmed is showing real data and trying to validate those types of things. So, but the question, Professor Ali, you mentioned, at least from my perspective, I think the cognitive radar and the cognitive radio, those will be bridged, right? Depending on, again, the role of the communication and radar, which one you would like to satisfy its function, and which one you can compromise its function to a certain degree. So, so that's an area a little bit different from the talk we just heard, which is certainly equally important. So, if I have a student, at least in the things I understand my area, I will ask the students to focus on the cognition aspect of RF technology.
Thank you very much, Professor Moeness. I remember in ICASP 2019, when I was with you and Dr. Azzeddin, I asked you a similar question, and you said integrated communication and sensing at that time. And I think it was a really timely topic. Okay, Professor Durgin or Professor Ahmed, anybody wants to add to the answer to the question? Do we have Professor Durgin?
I can take the first attempt at that question.
Yes, please.
So, you know, it's funny. My talk was very much a kind of a sci-fi talk in a way, in the sense that, you know, we're not going to build a space ambient power network next week or next year even, right? It's much, the technology readiness, as we like to say, is not as nearly as far along as a lot of other sensor technologies. But one of the things I try to make the case for the students, and of course, I don't know how KFUPM students are, but at Georgia Tech, everybody wants to save the world, right? You know, they want to have green energy sources from the sky and all these really cool things. that are kind of budding and just getting looked at. But the point is, each aspect of that system actually has a very powerful analog in existing technology that we are desperate for engineer training for, that we really want students in. So, you know, on the sensing side, on the ambient communication side, how do you make energy harvesting communication nodes? How do you communicate with very low power electronics? How do you use ambient scatter? That's a completely wide open field that people are just kind of getting into, and they still don't understand it. The communications, the physical layer stuff we're doing in that space, that has been done in that space, isn't that much more sophisticated than what we were doing in the 1960s with conventional wireless communications. So there's a tremendous room for growth in that area. On the transmission side, on spacecraft design, all of those are areas you can contribute to a really cool problem like space solar power, space ambient power. And, you know, there's a dozen employers waiting for you at the career agent fair at the end of the semester that really want your resume because you've built up all the skills that they need anyway. So any of those, focusing in on any of those areas is a win for the student.
Great. Thank you for your answer. The moment you said, or when Dr. Muhammad introduced you as a Virginia Tech graduate, I felt attached because also I graduated from Virginia Tech and I spent some time at Georgia Tech. And we'll hope that to see you all here at KFUPM. I would love to invite you here down to visit KFUPM. Dr. Ahmed, the floor is yours if you want to add.
Yeah, so yeah, just like following up more on the points I mentioned. So over the last, say, 4 or 5 years or so, like there was a lot of interest in machine learning in general wireless communications and sensing, and most of this research focused on a particular, let's say, data set, particular scenario, design machine learning models that works well and tune it to work well in one scenario. But then I think like the next, let's say 5 years or so, I think we're ready now to study the next level of questions, to ask the next level of questions about taking this really to practice in terms of the scalability of these machine learning solutions in real world, whether in sensing aided communication or in other also relevant wireless communication problems. So for example, if we look at this channel estimation or channel acquisition and beam management problems, if we design machine learning models, how can we guarantee that these solutions, these machine learning models will perform well in unseen scenarios? How to generalize the learning? Will you design one machine learning model that fits all scenarios, or will we have like will you be able to adapt these models for will we need to design different machine learning models for different scenarios? So the scalability and robustness of the machine learning model and operation, how the acquisition and integrating this into communication systems. So for example, when to decide that the data distribution has changed and we need to refine the learning, acquire new data. So those kind of interesting machine learning questions to really take the advantage and interesting gains of machine learning in wireless communication and communication and sensing to reality. I think this is quite interesting area for research, and with the availability of data sets, hopefully this is now, yeah.
Great. Thank you, Dr. Ahmed. I think we have Professor Henk here also. If he wants to add to this, the question was, if you were to choose a topic for your graduate students, a topic that will last for some time, do you have a prepared answer you want to add, Professor Henk?
Well, I can maybe just add a comment. I think a lot of very good answers have been given, but I also still believe in this convergence of communication, localization, and sensing, and to not see it as a zero-sum game, but everything operates over the same channel. So you should try to find synergies when designing these systems. And I think, for instance, coming from a communication engineering perspective, to look at what are the tools that people have used in radar, in GNSS, and channel modeling, and antenna theory, and AI, you know, and try to unify and improve on them, not just stick within your own kind of comfortable field.
Great. Frankly speaking to you, I would love to stay forever, but I think respecting the time of and the time difference, I think maybe it's too early at your side, and here at our side, our colleagues are already over hours. So I would love to see you here at KFUPM. I would like to invite you for coming visits, and if you allow me to conclude the session by thanking our team here in the center. Professor Dr. Mohammed Zahid, who chaired the technical committee, Dr. Wissam, for Dr. Mohammed Hassoun, and Professor Azzuddin for their excellent working on the speaker selection and arranging the technical side. I would like also to thank Dr. Abdul Majid Lawal and Engineer Pervez for their work on the support, on advertising the workshop and communicating with KICS. So any burning aspect, something that I forget before we conclude? Dr. Zahid, or can I conclude? Okay, then thank you very much.
I think you can conclude, Doctor.
Yeah, thank you very much, and we'll be happy to see you in future events. Thank you.
Okay, thank you very much.
Thank you.
Thank
you very much. All our invited speakers, thank you very much.
Thank you.
Okay, take care.
Thank you.
Thank you all.
See you. Thank you.
Thank you.
Bye. Assalamu alaikum.